that. So the reason why I wanted to chose this image for the opening image of the geological history of Canada. Firstly, does anyone know who painted this? Did you guys know this image? Good guess, but it's not. More from the Ontario region. This is painted by the painter Tom Thomson. Perhaps you've heard of him, a very famous Canadian painter who inspired the Group of Seven, who painted these very surreal, very kind of pastel-y landscape scenes of the Canadian Shield landscapes, primarily in one of the areas that I'm from, well, at least I frequented very, very regularly as a kid, and that is the Algonquin Park area of Ontario. And so this is a painting by Tom Thomson called Jack Pine, and they've actually kind of deciphered using this kind of like landscape forensics to find the exact location Tom Thomson was standing when he painted this image. And this was painted from a location in Algonquin Park. And the reason why I chose this is because this area of Ontario, like the area in northern Quebec and in northern Manitoba stretching up into the territories, is the Canadian Shield, which represents these extremely old, high-grade rocks that represent the heart of the North American continent, around which later continental fragments accreted. So around this area in Ontario and in Quebec and in Manitoba, this is basically the kind of geological heart, the geological continental heart of North America, around which all of the other material, including the United States, Eastern and Western Canada, and Northern Mexico, were accreted against this kind of initial fragment. And so we see these really old, really high-grade metamorphic rocks, felsic in composition, right? These really old continental rocks, which is the Craton of North America. These are cratonic rocks, right? Old, stable, continental root rocks. And so I thought it was fitting to display this image. And so as we continue, what we're going to do is kind of walk through the stages of the formation of Canada. And we're going to reiterate some concepts that we've talked about so far, like Wilson cycles and accretion. So in this lecture, a little synopsis here, we're going to talk about the important episodes in Canada's geological history, and we're going to kind of break them up into stages. As you'll see, a table for these kind of stages, for organizing these stages, might be very helpful. And I have an example of that in the slides that I'll show you soon. So I do suggest kind of either taking that slide, printing it off, or making your own table and kind of following along with these stages. We're going to talk about continental accretion again and how it built the continent. And we're going to talk about the significance of orogenic belts, right? Orogens, mountain belts, what do they represent? And what's their significance in this capacity? So just to set the stage a little bit, just to remind you of some terms we've discussed already. Craton is the old, often very highly deformed, stable, ancient core of a continent. So very, very old, stable, continental crustal rocks. And when those cratonic rocks are exposed at surface, we call this the shield. So the Canadian Shield is not the Captain America shield with a maple leaf on it. It is cratonic rocks exposed at surface. So sometimes these are referred to as basement rocks because they represent the root of the continent, the high-grade metamorphic or igneous rock or root of that continent. On top of those shield rocks, so on top of those cratonic rocks, we can pile sediments. So later, younger sedimentary rocks can pile on top of that. And so these sedimentary packages can sit on top of these shield basement rocks, and we call those platformal rocks. So a platform are basement rocks that are overlain by younger sedimentary units. So remember the law of superposition, right? Older rocks are below, younger rocks are above, higher in the sequence, unless everything has been overturned. Rest assured, the entire continent has not been overturned, right? So the law of superposition applies quite nicely here. So if we take a slice through A to A prime, so take a look at that little diagram in the bottom there, A to A prime. What we see are the Canadian shield rocks in green, or gray, whatever that color is, green it looks like. And you can see that as we move southwards, those shield rocks are progressively overlain by thicker sequences of sedimentary units, so platform rocks, essentially. And in the Grand Canyon area, right around where A is, so right around here, right in this area here where the Grand Canyon is, we can see directly down through those sedimentary layers, directly into the basement rocks. So at the very base of the Grand Canyon, we find these very highly deformed metamorphic rocks called the Vishnu schist. And this represents that basement cratonic unit that's overlain by thick sedimentary sequences that we can kind of see like pages of a book through the Grand Canyon. In Canada, in this area of Ontario and Quebec and into the territories, we don't have much sedimentary overburden. We don't have many platformal rocks in this area. You can see some start to accumulate over in the prairies and over into eastern Canada. But in the Canadian Shield area, this is exposed basement, right? So the numbers here are thicknesses, as you can see in the legend below, thickness of sedimentary units above the basement rocks, essentially. So it's thickening in certain areas, depending on where sediment is accumulating. A province, a geological province, is a subdivision of these cratonic units. Yes, that's right. It's in kilometers, Anna. So 1 kilometer, 2 kilometers, right? Thicknesses. And so a province, geological provinces, are these related subdivisions that are related to each other in either structure, in rock type, in origin. So there's some sort of commonality in a geological province. It's related to each other. It's related to itself in some sort of geological manner, right? Related to either geochronologically speaking, or structurally speaking, or compositionally speaking. And so a craton is made up of many geological provinces that are kind of welded together, right? Welded together through this process of continental convergence and accretion. A terrane is a specific term that we use for a distinct fragment of crustal material that's geologically related to itself in terms of composition and origin, that's accreted onto the side of a continent. So it's basically thrust up against the margin of a continent, much like we saw when we were talking about plate tectonics with respect to Eastern Canada, right? Like the Magma group and the Avalon terrane, which are basically accreted terranes that were pushed up against Laurentia, Paleo North America, during the formation of Pangea. Okay, so we're going to use these terms. We're going to refer to these terms as we continue. So then continents grow, as we've seen, by adding material, adding terranes onto their margins. So we'd expect the center of a continent to essentially be the oldest unit, right? The heart of the continent. And we're continually adding material to the margins of these continents, growing the continents in size. This is the process of accretion, right? And through accretionary events, we're always forming orogenic events, right? Because we're basically, this is convergence, continental convergence. So we're pushing fragments into each other. And so we generate mountain ranges, either through continent-continent convergence, like in India and Asia, where you see the Himalayas, continent-continent convergence forming the Himalayan origin, right? Or this can also be exacerbated by the formation of continental volcanic arcs, right? Like we see in South America with the formation of the Andes, right? We see an origin there as well, the Andean origin. But those mountains are kind of the result of both accretion and volcanism, right? It's a continental volcanic arc there as well. So when we have convergence, we're forming orogens. And there's a question here in the chat. So would the accreted terrain be terrain formed after the split of Pangea, or did it exist during the time of Pangea and then ended up accreting? I'm not quite sure I understand, but terrains are accreted through convergence, right? There's no other way you can push something up against the side of something else without convergence, right? So convergence either in the form of ocean continent subduction primarily, right? Where we have ocean subducting underneath continent, and whatever's sitting on top of that oceanic plate that cannot subduct will accrete, right? So this is always a convergent phenomenon. And we form orogenic belts in this manner as well. Like the Appalachian belt and like the Canadian Cordillera, which is the youngest units to accrete onto North America. Sure. So the evidence that we have from these orogenic belts is very highly deformed rocks, right? Wherever we see very highly deformed, very high-grade metamorphic rocks, this suggests orogeny. This suggests mountain forming, right? There's no way that we could deform these rocks in the manner they are deformed, or metamorphose these rocks to very high grades, meaning very high temperatures and pressures, without being in the heart of an orogenic belt, right? Very deep into the roots of mountains, we have very high temperatures and pressures. And so this influences the rocks, right? This influences the fabric and structure of the rocks. It deforms the rocks, and it can change the composition, the mineralogy of the rocks. And so these rocks can be very highly deformed. So whenever we see rocks like this, and a very high-grade metamorphic rock is called a gneiss. So these are what we refer to as gneissic rocks, high-grade metamorphic rocks. This suggests that this was formed through continental collision, right? Or accretionary events, some sort of convergence. So geologists can use the presence of these high-grade metamorphic rocks to indicate something about the tectonic past of that environment. Like in Ontario, in the area that Tom Thomson was painting that painting, those are very, very high-grade deformed metamorphic rocks. There's no way we can form those near surface. There's no way we can form those rocks anywhere but deep in the heart of an orogenic belt. And so seeing those rocks now exposed at surface tells a geologist something about the tectonic past, right? This area, once upon a time, must have been an orogenic belt. There must have been an origin here that is now penoplaned, that is now eroded away. And so we're seeing the roots of those mountains now exposed at surface. And so in this image here, we can see 3 different units of rock that have been metamorphosed all under the same conditions, right? So if I had a layer of basalt and a layer of sedimentary rock on top of that, and then a layer of igneous rock on top of that, and I subjected them all to the same metamorphic conditions, all 3 of those rocks would be metamorphosed to the same grade, right? They're all subjected to the same metamorphic conditions in the heart of a mountain belt. And so in this image here, we see these metabasalts, we see metasedimentary rocks, and these metamorphosed granites all beside each other, because that's how they were initially primarily deposited. But now they're all just metamorphosed. And so when I say very highly deformed, this is kind of what I'm talking about here, right? This is a high-grade metamorphic rock. Rocks do not form like this primarily as an igneous or sedimentary rock. This very convoluted fabric is a result of metamorphism. And we're not going to get into why this fabric forms and what this rock specifically is in this course. That is a topic for Geology 1200, and I encourage you to take that if you haven't already. It's a great course. And I say that maybe partially biased because I teach it. But this represents a very, very convoluted, very highly deformed, high-grade metamorphic rock. So this is the type of material that we see forming deep in these crustal roots. That's a good question, Hannah. So the scale we probably see here, if I were to have to take a guess, I bet the scale is below that text box. that's probably like a foot or so. That's maybe like 30 centimeters right there, give or take. We can see these on broad scales. We can see these on small scales as well. So just to remind you of this whole process, we're going to be referring to several Wilson cycles here. This is how these continents are growing, right? Through Wilson cycles. And through Wilson cycles, we get this kind of, remember, we get kind of continental rifting, right? And this continental rifting, like we see in East Africa today, will eventually evolve into a marine basin, right? Like we see in the heart of the Atlantic today. Right? And so this evolves as a divergent boundary setting underneath an ocean. Eventually, that spreading will stop and the closure of the ocean will proceed. And as that ocean is closing, terrains can be accreted. So we always see these images here that show these really nice ocean basins with nothing in between, like these ocean basins right here. Right? There's nothing in there. But keep in mind that in that ocean, we can have microcontinents, we can have volcanic island arcs, we can have seamounts, and all of that material will not subduct. So when the ocean is closing, all of the material that's in that ocean, either in the form of a microcontinent or volcanic island arc, will accrete. And these are how continents grow. And so with respect to Canada, we're going to talk about four main stages, four main Wilson cycles that led to the growth of Canada. So in Canada, the geological record points to at least four Wilson cycles that have grown the North American continent. And this includes essentially four supercontinents, if you will: Arctica, Nuna, Rodinia, which we've kind of already talked about a little bit, and Pangea, of course, which was the most recent supercontinent. And now we're kind of in the middle of a Wilson cycle. We're right in the stage that I circled there, stage 3. And so with respect to North America, we're going to split this up into fragments. And you can see that some of these fragments are numbered 1 through 5. And these fragments added onto the North American continent through this kind of Wilson cycle and accretion process over, the 3 billion years that this occurred. So we're going to start with Arctica. This represents that ancient root of North America. You can see where basically Northern Ontario is up in here, and Northern Quebec up into the provinces, right? So this is all the ancient root of North America, around which all of these later units accreted. And this was about 2.5 to 1.9 billion years old. Arctica formed. Later, this fragment here was added to this. So this is generating a new supercontinent that's often called Nuna or Nina in Canada, at least. Sometimes it's referred to as Columbia in the United States. So, depending on where you are geographically, these may have different names. In Canada, we often say Nuna. And this was essentially the result of a second Wilson cycle that formed a new supercontinent. And now keep in mind that, back in the ancient geological past, let's say 3 billion years ago or so, we don't have a very good constraint on when and how plate tectonics started and what plate tectonics actually looked like. Did plate tectonics look quite similar to how it looks today, or were these processes slightly different? Were the rates slightly different? What did the plates look like? Plates are in a state of flux, right? So the lithospheric tectonic plates that we have today were not always the same tectonic plates that we had in the geological past, nor will they be the same that we have in the geological future. Plates are also in a state of flux, so we don't really know necessarily what the tectonism looked like back then and when it actually started. After Nuna formed, we accreted the Grenville material here. So this is called the Grenville orogeny, and it's called an orogeny, remember, because this is a mountain chain. And so this would have been the mountain chain that was produced as a result of forming Rodinia, the supercontinent that predated Pangea, so the predecessor of Pangea, which formed about 1.3 to 1 billion years ago. And these are the very, very high-grade rocks that Tom Thomson was standing on when he painted his painting. So in northern Quebec, up and even into the Gaspé, and in Algonquin Park, which is right about here, right about there. It's hard to see where I just drew that, but right in there. That represents these high-grade rocks that were at the heart of a mountain belt that was formed as a result of Rodinia amalgamating, much like the Appalachians formed as a result of Pangea amalgamating. Then we have Pangea that came together about 600 to 300 million years ago or so, and then started splitting in the Cenozoic, or sorry, in the Mesozoic. So in the late Triassic, early Jurassic, we started to split Pangea apart again. And now, in the middle of a new Wilson cycle, we've accreted the material on Canada's and the United States' western coast. So this is the newest material to accrete against the North American continent, about 250 million years ago or so. And now we're going to go through each one of these stages in some more detail sequentially. So remember the example from Pangea, right, from the Appalachians, and we will talk about this in more detail next week. However, just to remind you, all of the terrains that we have here in Atlantic Canada are accreted terrains, right, including the Humber, the Dunnage, the Avalon, the Magma terrain, the Gander terrain. These are accreted terrains and sedimentary packages that have been thrust up against North America's margin. And in doing so, we're generating an orogeny. Right, we're generating a mountain belt. These are mountains, right? Don't be fooled by this, right? This accretion and orogeny are very related terms, right? Through accretion, remember this is convergence, right? We're smushing terrains up against the margin of a continent, and in doing so, we're thickening the crust. We're thickening that unit of crust. When we thicken crust, we form orogens. Right, we form mountain belts. So this was the Appalachian origin. And now this has been penoplaned, right? The Appalachians have been eroded down, especially in this northern area of the Appalachians. But we see evidence of that through the presence of metamorphic rocks and deformed rocks. We'll come back to the Appalachians again later, though, of course. So I want to reiterate that plate tectonics is, now widely accepted and very widely understood with the technology that we can use to investigate plate tectonics today, such as seismic tomography. However, we still don't have a very good control on when plate tectonics actually started. So considering that they may have started in the Archean, this poses a lot of questions, right? It's quite a contentious issue. We don't know, firstly, for sure, how continental crust got its origin. Continental crust, and remember when we were talking about plate tectonics a little while ago, I expressed two theories of where continental crust came from. However, there's a little bit of a chicken and an egg sort of problem here with this issue, right? One of the theories states that continental crust began with plate tectonics. As we get plate tectonics, we get subducting crust, we get partial melting through flux-induced melting, hydration melting. That generates these magmas, which can ascend to form magma chambers and then, batholiths, plutons, which represent this kind of primitive continental crust. And so we're developing continental crust through plate tectonics. But how did plate tectonics actually begin? Right? Because in plate tectonics, we have subduction of denser material under less dense material. And so how did that start? The other theory of where continental crust came from is that it formed initially as this kind of thin rind, or potentially through these kind of mantle plume environments like Hawaii is today. So Hawaii is nowhere near a plate boundary. Hawaii is right in the middle of the Pacific plate. And Hawaii is generating vast amounts of magma. And so that magma can feed the surface to form lava flows. That lava is mafic in composition. The mantle is ultramafic in composition, right? So already we're getting a little bit of a chemical differentiation and a density differentiation, right? The material of Hawaii is less dense and compositionally distinct from the material of the mantle. So it's theorized that some of the first continental crust to be produced was rather mafic on average, similar to the oceanic crust. And so maybe the first crustal material to speak of was very similar to oceanic crust in composition, but still of a low density to kind of initiate plate tectonics. Two theories with the advent of plate tectonics is in the modern style we know, right, with a subduction zone pulling down another plate. However, with plate tectonic theory, there is still some unknowns with mechanism, right? Is this plate right here kind of riding over top of that plate, or is this plate down here, the subducting plate, pulling the rest of that plate downwards? Now, it's probably a little mixture of both, but there is a very well-established theory called negative buoyancy theory with respect to plate tectonics. So this states that as this subducting oceanic lithosphere is subducting and being pushed into the mantle, the temperature increases, the pressure increases, and we get this very dense, high-grade metamorphic rock called an eclogite. These eclogites are dense enough to pull the rest of that crust downward. So there's a bit of a negative buoyancy effect, and there's a force pulling that slab down into the mantle. And so it's a bit of a slab pull sort of mechanism related to negative buoyancy. However, how did we produce the first eclogites without plate tectonics? Another chicken and an egg problem, right? How do we initialize negative buoyancy without having plate tectonics to begin with? Because we can't produce these high-grade metamorphic rocks with this negative buoyancy effect without subduction zones. So there's that chicken and an egg problem again. Another theory as to how plate tectonics might have started is related to this kind of drip mechanism, where potentially we're kind of forcing locally plates together, and it's forcing some material downwards, and that material being forced downwards potentially might be metamorphosing into denser rock, which is kind of pulling these sinkers downwards, right? And so maybe this starts to initiate the first kind of rudimentary, very primitive plate tectonic situation. So yeah, it's still a bit of an unknown, and we still have a lot of unanswered questions. And so this is, I think, one of the beauties of geoscience is that, you know, even though we're studying very, very old systems and very old rocks, the theories are very new, right? There's still a lot to be understood in the geosciences. And, you know, maybe we won't see these questions answered in my lifetime or, you know, older geoscientists' lifetime, and it might take, you know, your guys' generation to kind of answer some of these questions. It's a very dynamic science. There's still lots to answer. Well, plate tectonics is a theory, meaning it is proven, right? We can observe plate tectonics happening now, but we still don't know exactly how it started. Sorry, I'm answering a question posed in a private chat here. It is proven to be occurring, and we have evidence that plate tectonics is indeed happening, 100% for certain, but we still don't necessarily know its origin, how it got started, right? Mars and Venus don't have plate tectonics. Why don't they have plate tectonics, right? This might have something to do with the uniqueness of Earth with respect to water, the presence of standing bodies of water for extended periods of time. Maybe that had something to do with it. But we still have yet to unequivocally answer that question, why Earth has plate tectonics and how they got started, and why Venus and Mars did not. So there's a lot of contention around this issue, and these are some research. This is some published research that kind of peg plate tectonics, the start of plate tectonics. You can see that it kind of floats all over the Archean. So it is theorized that plate tectonics actually did get its start in the Archean in some sort of primitive way. But there's some researchers that posit that plate tectonics started much later, for instance, in the Proterozoic. So, only a billion years ago or so, maybe plate tectonics in the form we know it got started around then. There's still some contention around this issue in the scientific community. So this is a table that I was referring to. I think it'll be wise to generate your own table and follow along in this fashion, right? So as we talk about these stages, fill in the blanks. And I've kind of done one for you, for instance, the formation of Rodinia, just so you can kind of understand what to expect and kind of what to fill in. I think it's a good idea to do this because we're going to talk about several stages of the formation of Canada. So in order to kind of wrap your mind around these stages and kind of pull out salient information from this material, put it in a table like this. So I'm starting with what I'm going to call stage 0. And I'm calling it stage 0 because Arctica hasn't necessarily formed yet, but the beginning stages have. So stage 1 will be the formation of Arctica. But Arctica formed through the amalgamation of smaller microcontinental units. These smaller microcontinents kind of came together, amalgamated together to form this very first primitive supercontinent that we call Pangea, or not Pangea, Arctica. And that was way down here, somewhere in here, right? Where the very first, most primitive rafts of continental crust are forming. And we have evidence of some of this extremely primitive crust in the form of, for instance, the Acasta gneiss. So the Acasta gneiss is in what's called the Slave Province. And so here's that word, right? Geological province. The Slave Province is a geologically related unit of rock, and it's related to each other in terms of the rock types, the structure, and the origin and development of that unit of rock. There's some other provinces here as well, such as the Superior Province, the Ray Province, as you can see here, the Nain Province, etc., right? These are related geological units that, in the case of the formation of Arctica, have kind of come together, amalgamated together. Yeah, it's an unfortunate name, I suppose, and this was pointed out in the chat here in today's climate, but it wasn't named that as a result of servancy. Obviously, it was. I'm not sure why it was actually named that. It was either related to Inuit term in the area, or maybe someone's name who first studied this. That's how the Ray province came to be. The researcher that named that geological province was Ray, R-A-E, and so the Ray province is named after that individual. So yeah, they get their names. However, we just have to separate ourselves from politics, of course, right? We can't let politics dictate the progress of science. We have to be careful with what we do and what we say to a degree, of course, but yeah, it wasn't named that in today's light. But what I wanted to draw your attention to in the Slave Province is that it has the oldest rocks that we know of in Canada and in the world to some degree, for that matter. So in the Slave Province, we have a rock type called the Acasta gneiss. And now the Acasta gneiss in the Northwest Territories is essentially the world's oldest rock at about 4.03 billion years old. And so this is before the Archean, right? Or like right at the beginning of the Archean. And so we don't even know what plate tectonics looked like back then, let alone if plate tectonics was actually a relevant factor in the formation of this rock. However, this rock resulted from the metamorphism of a granitic rock. So this tells us that despite what plate tectonics was doing and what it actually looked like, there had to be some sort of granitic rock around, right? So granites, the rock type that makes up the average composition of continental crust, were being generated back in the early Archean. But not only were granites being generated, they were being metamorphosed. This rock is a very high-grade metamorphic rock, right? So how did we metamorphose this rock? Not only does this rock, this metamorphic rock, date to 4.03 billion years, but if this is a metamorphic rock, that must mean that the metamorphic rock must have come from the metamorphosis of a parental rock, right? You can't metamorphose something that doesn't exist, of course. We need a parent rock to metamorphose. So this tells us that there must have been an even older granitic parental rock that predated the Archean, that was metamorphosed to form this 4.03 billion year old metamorphic rock, right? So really intriguing findings here related to the early Earth continental crust formation. The reason that we know the age of this is through geochronology, right? Radiometric geochronology, finding these little minerals called zircon in here, which are very robust minerals. They're very chemically insensitive minerals, so they do not weather very easily. They last a very, very long time, as you can tell. And zircons have an interesting characteristic in that they can uptake uranium and exclude lead. And so once we reach the closure temperature of that zircon, the radiometric clock starts, right? After we pass the closure temperature, as we go below the closure temperature or at the closure temperature, no more diffusion of uranium and lead can occur. And so this is when the clock starts. Uranium decomposes into lead, and we can time that clock by understanding the composition of these zircons. There was a question here in the chat. Maybe Hannah, flip over to public just so I don't have to reiterate that each time. She asks, are zircons the best way of dating oldest rocks on Earth, or are there any other minerals used? Yes, they definitely are the best. They are the most chemically insensitive, they are the most robust, and they're very common. They're common in igneous and metamorphic rocks. And so they're a great tool to date rocks. However, we do have some other minerals that we can use as well, but they can be a little bit more sensitive to temperature fluctuations and chemical alterations. So there are some systematics that we have to kind of pay attention to. And I don't want to necessarily say less accurate, because the date will be accurate, but we do have to understand where that date comes from. Let's say we have a mineral that reaches its closure temperature and then it starts decaying in a normal fashion, but then another sort of volcanic event happens, or another metamorphic event happens that reheats that rock. So now that mineral will go above its closure temperature again, and it will be reset. And so the temperature will be accurate, but it'll be a reset clock, because the closure temperature has been gone over again, right? And then came back down. So we need to understand a little bit about the system before we kind of make these broad conclusions. And yeah, so we would, do several dating techniques, for instance, with different minerals in that system, compare them, contrast them, maybe look at rocks that are in the vicinity as well, and compare them to those additional rocks in the vicinity. There's lots of tools that we can use. And so this is the paper, one of the papers that was published relating to dating those zircons in the Accastanites. This is a 2006 paper by some Japanese researchers. And these Japanese researchers dated the zircon in the Accastanite complex. And they found that this zircon, this was from Yilgarn, Australia. So this zircon in Australia now dated to 4.2 billion years. So the zircon itself is older than the Accastanites. But what's interesting about this is that this rock must have resulted from older granitic rock. There must have been rock there to be metamorphosed. And so this just kind of reiterates that point I was mentioning. Okay, so back to stage 0. We're setting the stage for the formation of Arctica. But first we need continental material to amalgamate, to come together, to form Arctica, right? We don't exactly know what the Earth looked like this long ago. We do pretty good jobs of tectonic reconstructions in the more recent geological past, you know, 1 billion years and later type of thing. But, you know, once we get over 1 billion, 2 billion years, we really don't have a good constraint, a good understanding on what the Earth actually looked like in terms of its tectonism. And so we don't necessarily know how all these came together. But we do know that they did, of course, right? We see it preserved today as the North American Craton. And so these units, including the Slave Province, the Ray and the Hearn Province, the Nain Province, and the Superior Province, and you don't need to memorize all of those names, but I just wanted to show you that, you know, we have these microcontinents that have amalgamated together. How did they amalgamate together? What process here is at work? What process must have been at work to push all of these continental units together? Right. Plate tectonics in whatever primitive fashion. But more specifically, let's not call it explicitly plate tectonics yet. Let's just call it convergence. Because I'm not exactly sure what it looked like. We don't exactly know what it looked like. Maybe, you know, the beta version, plate tectonics beta version, whatever that looked like, amalgamated this material through continental conversions. And this was about 4 to 2.6 billion years. You can see that there's a pretty big time span here, right? How? This is what I just asked. Continental collision, right? The convergence of these continental units, forming orogens. We have direct evidence of continental collision in the form of what are called greenstone belts. Now, greenstone belts, this is the Superior Province, and we're going to use the Superior Province as an example. So this unit right down here is the Superior Province. Here it is here, outlined very broadly with respect to granites and gneisses in pink, greenstone in green, and greenstone represents a basalt that has been altered or metamorphosed. And so greenstone is mafic material that has been altered. And when that material alters, it forms a green rock, which is why it's called greenstone. I'm going to show you a sample of it in just a moment. The yellow units are metasedimentary rocks. So sedimentary units that have been metamorphosed, okay? Notice the morphology, notice the shape of those greenstone belts here. And we're going to talk about why this is in just a moment, but I want to draw your attention to the fact that they kind of represent these kind of broadly parallel linear units, right? There's these long stretched out linear units separating units of gneiss and granite. So here's, you know, a unit here separated by a greenstone belt from this unit right here. You can see that we have one here separated from this one, separated from this one, right? And in between these granitic and gneissic pink units are these kind of elongate greenstone belts. What does this even mean, right? So to answer your question, Saray, it's not just one big gneissic unit. I mean, there are many subdivisions in here, right? So this is the very broadly speaking. We can have all sorts of different granitic and metamorphic rock types in these units, but in the broadest scale, they're high-grade metamorphic rocks or igneous rocks or felsic igneous rocks. So they're kind of like granitoids, and they can be all sorts of different granitoids, tonallites, monzogranites, granites, diorites, right? All sorts of different granitoids or high-grade metamorphic rocks. But we're not going to go down that road in this course, of course. So yeah, Hannah's touching on it here a little bit. But before that, I'd like to show you what a greenstone looks like. So I think I told you guys that I did some of my PhD research up in the Canadian Arctic, and there's a gold deposit up there called the Hope Bay Greenstone Belt. And so these gold deposits occur in the Hope Bay Greenstone Belt, and it's called a greenstone belt, which looks similar to the ones I just showed you in Superior, because it's green. So look at how green that is. This is a basalt, or at least it used to be. And now it's very highly altered. The reason why it's green is because some of the minerals inside of a basalt can alter to a mineral called chlorite. The mineral chlorite is a mineral that's characteristically very green. And so you can see that a lot of that basalt, which starts its life as a black rock, is now green because of the alteration. You can see that the outside of this rock is very strongly altered. You would really have no way to tell that this is a basalt without, popping it open and taking a look on the inside, because it's just very, very altered. You can see this kind of beautiful lichen growing on it. It's a very pretty rock just at face value. But you can see that it's very highly altered. You can see this alteration rind around it as well. Right, so very old, very weathered. This rock is about 2.6 billion years old, an old greenstone. So this is why we call it a greenstone belt. This started its life as a basalt, but it's now an altered basalt, a metabasalt, if you will, metamorphosed in altered basalt. And when we do that, it tends to go to this green color. And peridotite, to answer a question in the chat, I'm going to get to that in a few moments, but I have a sample here in front of me. Peridotites, ultramafic rocks that are in the mantle, tend to weather and look like this. So recall when we were talking about the ophiolites in Newfoundland, they look like this. This is the color of them, right? When we saw that satellite image, those hills looked like this rusty brown. That is peridotite. This is what altered peridotite looks like. The inside of that peridotite, you can see, does have this kind of dull, black, kind of gray, green sort of alteration. And so this does not look like what it would look like in the mantle. This is very highly altered. Peridotites alter very, very easily, but we're going to come back to those. Okay, so greenstone belts. Notice that they're linear. Notice that they're separating smaller felsic units, granitic or gneissic units. Why? What do they mean? So the significance of a greenstone belt is that, as Hannah kind of alluded to here, it represents units of accreted ocean floor or volcanic arc complexes, island arc chains. So this is why they're kind of smushed out in between microcontinental rafts. Now, take a look at this little cartoon I drew. So this is really, really basic, but it gets the point across. I have a microcontinent here, call this microcontinent 1 and microcontinent 2 in pink, okay? And now we have some form of subduction. Remember, we don't exactly know what plate tectonics looked like back then, and the rates and the forces and the mechanisms. But let's just assume this is the case. So now we know there was convergence at least, right? So now we have this subduction, and we have this green. Let's just use green because it's a greenstone belt unit subducting under that microcontinent. Right? Felsic material, more buoyant than mafic material, it's being subducted underneath. The yellow units represent sediments, either this accretionary wedge sediment here, right here, so accretionary wedge sediment, active margin sediment, or this passive margin sediment right here. This little green hump right here represents, let's say, a seamount or a volcanic island arc complex, okay? In other words, material that won't easily subduct. And so what happens as we converge these two plates? We approach a situation like this, right? They're getting closer and closer. Everything is getting sandwiched in between. Eventually, we have convergence and orogeny. So we sandwich that material in between now. Now we have unit number 1 and number 2, and in between we have the sediments and the basaltic units sandwiched right in between, right? And here's a mountain belt. This is an orogenic belt. Now I peneplane it, and I cut the top of that off. Now I've cut the top of this off, and now what happens if I look at it from the top? It might look something like this, right? We see these smaller units. So here's unit 1, here's unit 2, these microcontinental units, and between them, the material is sandwiched in between. The sedimentary and mafic material that was in this ocean basin, or this basin in between, has now been sandwiched in between the two smaller microcontinental units. Okay, so this is what a greenstone belt is, and it's called a belt because it's this kind of broadly linear feature. And so if we flip back here, you can see that what the superior province actually represents is the amalgamation of even smaller microcontinental units, right? With greenstone and sediments sandwiched in between them. So we're amalgamating microcontinents into larger microcontinents, which eventually will amalgamate into larger continental fragments, right? The growth of continents. Does that make sense with everyone? Greenstone belts. Awesome. Okay. So it's simply the same processes we've been talking about here, right? There's sediments, there's volcanic island arcs. This material will not subduct. And so it's sandwiched in between. It's accreted into this orogenic belt. If we peneplane that origin and we look at it from the top, we see something that looks like this on the slide, right? An orogenic belt in between, which in this case we call a greenstone belt because it's dominated by these altered mafic rocks. And so there you go. That's exactly what we're looking at right here. So there's plenty of evidence that there was active metamorphism and active volcanism during these events, right? If we have subduction of oceanic crust, well, then we get magma generation, right? They're part and parcel. How are we getting magma generation via subduction? Why are these related? Think about that for a second. Not necessarily accretion, right? Because accretion doesn't necessarily generate magma. But how are we generating magma at convergent boundary settings? Exactly, right? Subduction, and then the process of hydration melting, right? Hydration melting takes place. That's how we're generating a magma, right? Through hydration melting, in subduction zones at least. And so when we see these vast volumes of felsic material, of granite, like we see here in Nova Scotia, this is direct evidence for partial melting and subduction. In this area, in the Appalachians, this area of Atlantic Canada, we have a large body of granite, the South Mount Batholith, right? If you walk to Peggy's Cove, for instance, or Terrence Bay or wherever, you'll find this granite. You're standing on it today at Peggy's Cove, for instance. That granite only got there because of subduction-related partial melting of that unit, right? Hydration melting. That's the only way it was there. What that granite represents is a fossilized magma chamber, if you will, a frozen magma chamber, right? That magma chamber is now solidified and frozen in the crust. When it was initially forming, this would have been, 5, 10 kilometers down in the crust as a magma chamber, which was potentially feeding volcanic vents at surface. And now we don't have any remnants of those volcanic vents anymore, right? We've eroded all of that away in Nova Scotia. And so now we're basically standing on the magma chamber that would have been 10 kilometers down at the time of formation. But the presence of that batholith, the presence of that magma chamber, indicates active magma production. How do we get active magma production? We can't just get it in any old place of the crust, right? We need to have active plate tectonics generating this magma. In particular, we need to have convergent boundary associated magmatism, because at divergent boundary settings, we do not produce felsic magmas, right? So this suggests a convergent boundary setting. And that's why we see the granitic batholith, South Mountain batholith here in Nova Scotia during the formation of Pangea off the coast of Nova Scotia was a convergent boundary, right? This was a subduction zone around here. And so there was active volcanism in Nova Scotia, New Brunswick, Newfoundland during the formation of Pangea. And the evidence is right here in the rocks, right? Meteors can certainly give rise to magma generation, but this is a very, very distinct magma generation. We get what are called layered intrusions, these kind of layered intrusions, because we form a basically a pool, a big magma pool that kind of layers and settles out, much like Sudbury, for instance. So very distinct and very identifiable in the case of meteor or meteorite magma generation. So despite the fact that these rocks can be incredibly old, we can still garner some information, primary information from these rocks. So these rocks are about, well, how old are these rocks? These are Archean, so over 2 billion years old, these rocks. But we still see primary features, primary sedimentary features. Look at the sedimentary rock here. This is a sandstone. You can still see evidence of cross-bedding in this rock. Right? You can still see the layering in that sedimentary rock, despite the fact that this has gone through geologic hell, veritably speaking. We can still see evidence of primary sedimentary features there, right? Look above. We see evidence of pillow basalts, right? Archean pillow basalts, and we see the rinds around those pillows. So here's that kind of quenched rind around the pillow there. We can see a rind around this pillow. So really, really old pillows. What do pillow basalts indicate about the formation of that basaltic lava? Volcanism, but where? Was this terrestrial or was this submarine volcanism? Underwater, Hannah pointed out in a private chat here. Underwater. This indicates that it had to be submarine, right? It had to be submarine because that's where we form pillows. We form pillows because they're quenching very quickly in interaction with the water. So right off the bat, right with this evidence right here, we can tell, we can kind of get some information using these primary features where this rock was formed and how it was formed. This rock here is very special. It's called a komatiite. And a komatiite is like a basalt, but ultramafic. So imagine taking some of the mantle, and melting it wholesale, melting all of that chunk of the mantle, and then solidifying it. This is what you'd form, a komatiite. So a komatiite is an ultramafic lava flow. It's an ultramafic lava. So basalt is a word that we give to a mafic rock, right? A mafic rock as a result of a lava flow at surface. Good question. How would we get an ultramafic lava? If we melt some of the mantle today, say at a divergent boundary, right? Decompressional melting. We partially melt some of the upper mantle, but what sort of rock do we get when we partially melt some of the upper mantle? A mafic rock, bingo, like a basalt, right? So we see a compositional difference here, right? We can't entirely melt the ultramafic mantle because we don't have enough temperature, right? It takes a lot more temperature to entirely melt the upper mantle, but we can melt some of it, some of the lower temperature minerals. We can melt those, but when we melt those and separate them from the upper mantle, it forms a mafic melt. And so you would expect then that a felsic melt melts at a lower temperature, as indeed does. So as we go from ultramafic, mafic, intermediate, felsic, the melting point goes down. So we cannot melt the upper mantle wholesale anymore. Why? What has happened? What has changed? You will never find this rock on Earth forming today. What happens to your cup of tea when you leave it on the counter for too long? Same exact thing happens to the Earth, right? It cools. So when the Earth has formed, when the Earth initially formed back in the Archean, it was much hotter. The Earth was much hotter, about 300 to 500 degrees Celsius hotter in the upper mantle. And so with that increased thermal energy, we can melt some of the upper mantle wholesale, forming an ultramafic lava. But today, the Earth is significantly cooler. And so we don't have the temperature required to form ultramafic melts. We only have the temperature necessary, or the temperature to form mafic melts. So these are very special because we do not form them on Earth anymore. There are locations in Ontario that you can find these preserved komatiite flows in the Superior Province. And they're protected now. You can't go and just willy-nilly sample this rock. They're protected areas because there's only so much of it that we have preserved on the surface of Earth. We don't form these rocks anymore. The interesting texture that you see there is related to the growth of pyroxene and olivine crystals. It's a texture called spinifex, and it's very characteristic to komatiites. Really unusual textures. When we have this kind of cooling ultramafic lava, as it's flowing along, olivine and pyroxene crystals, which are two of the dominant crystals in the mantle, tend to kind of grow in this radiating needle-like fashion. So I'll show you some of that rock right now. So this is komatiite. Doesn't look very impressive, right? Just looks like kind of a ordinary black gray rock. And it is quite ordinary, but we don't form this anymore. We do not form this rock on the surface. Oh yeah, I have plenty of ultramafic rocks in my office, actually. This one here is a komatiite, and it's very highly altered, as you'd expect. And so this is mostly talc now, which is one of the most soft minerals in the that we know of, essentially, right? So it's number 1 on Mohs hardness scale, very soft mineral. So you can actually scratch that with your fingernail. Talc, like in talcum powder, exactly. Baby powder is talc. It's a mineral. And so when ultramafic minerals alter in the presence of water, we tend to form this mineral here, talc. And so this is a komatiite. This is an ultramafic lava flow. You don't form these on Earth anymore. I showed you an example of this. Actually, I'm going to grab something here. Just give me a second. So here is peridotite. This is what the mantle looks like. So you can see these beautiful green crystals of olivine and these black crystals of pyroxene. This is what the mantle looks like unweathered, exactly. So this is unweathered, fresh mantle because it's been brought up rather recently in basalt erupting from the upper mantle. And so this is nice, fresh upper mantle. But if we leave this material, because it weathers very, very easily, geologically speaking, if we leave this material for, you know, a couple million years, it'll end up looking like this. This kind of bland, kind of khaki tan colored rock. And this weathering material that you see here is a mineral called serpentinite. And so when these ultramafic minerals weather under special conditions in the presence of water, we can form another mineral called serpentinite. And so we can form talc as well. So there's definitely talc in here, but there's also this kind of greenish mineral serpentinite. So this is what weathered ultramafic rock looks like. Very, very weathered. And this is from Newfoundland, this one here. So these are from the Table Mountains, from the ophiolite of Newfoundland. And so this is what the upper mantle looks like. And this was sampled from Newfoundland in that ophiolite sequence, right? So you can basically walk right through the moho in Newfoundland. Yeah, so what do we have left here? Okay, so let's just finish up. We only have a couple minutes here, and so I'm going to leave it at the beginning of Arctica, which is stage 1. So we've talked about now the formation of these microcontinents, right? We've talked about the amalgamation of these microcontinents into Arctica. So these microcontinents in and of themselves were manufactured by smaller microcontinental fragments, smaller continental crustal fragments coming together. And we have evidence of that in the form of greenstone belts. So if you're asked a question on a test or a final about the significance of a greenstone belt and what it actually represents, you'd be able to answer it, right? That's what greenstone belts represent. So, direct evidence of continental convergence. So, stage 1 then is the final amalgamation of these microcontinents into Arctica. And this was theorized to be complete, about 2.6 to 2 billion years ago or so, which is when the final accretion of Arctica and maybe even the start of the breakup of Arctica formed. And so now we're floating around right here in the Archean. Okay, so we're moving our way up the geological timescale and looking at these Wilson cycles as we go. And so I'm going to leave it here. Way back here, we had evidence of glaciation. 2.5 billion year old, 2.4 billion year old glaciation. So probably like a snowball Earth sort of situation. That evidence comes in the form of tillites, right? So lithified rocks formed from lithified glacial sediment, till, in other words. How do we know how old they are? Excellent question. It probably takes a lot of sleuth work, detective work in terms of relative dating and absolute dating of zircons and clasts like these granitic clasts that are locked inside of there. But keep in mind that you can erode anything of any age. So dating that granite won't give you the age of the glaciation, of course, right? So we have to use other techniques to date these rocks as well, such as relative age relationships, cross-cutting relationships, things like that. Take a look at the right image. We see striations. Those striations post-date that 2.4 billion year old glaciation. Those are much, much later. That's much later evidence of glaciation. So in that image in the top right, we see 2 glaciation events, likely separated by billions of years, hundreds of millions of years, right? So the tillite that you see here, that rock that the hammer is sitting on, is evidence of this 2.4 billion year old glaciation event. And the striations you see on the surface of it are a much younger glacial event. Yeah, so we probably had 2. It looks like this was the dominant motion in this direction. But there might be some evidence of maybe some ice moving in that direction as well. Or it might just be jointing. It might just be natural breakage in the rock. We want to see repetitive striations. So, but yeah, let's leave it there. I'm sorry if I kind of went off on some various divergences, but there's a lot of stuff in this lecture. We're putting everything together here. We're kind of talking about all sorts of aspects of stuff that we learned about in this course, from glaciation to plate tectonics to accretion to Wilson cycles to structure. So I'm glad you found them interesting. Hopefully everyone else agrees. Any questions, guys? Okay, let's flip to this. Okay, so we stopped about here, and we were talking about stage 1 being the final accretion of Arctica, which is essentially the first supercontinent that formed, or at least that we have evidence for the formation of. And I also mentioned that even way back here, 2.5 billion years ago in the Archean, we have evidence of glaciation as well. So very ancient snowball Earth type of glaciation. So here is your ice question number 1. What origin welded Arctica together? Now this origin is what we call the Trans-Hudson origin, or the THO. The Trans-Hudson origin passes through kind of central United States, up through the Hudson Bay area and into the territories and into the Arctic archipelago. And so this was the origin that kind of welded together many of these microcontinental fragments to generate Arctica. And as you can see, Arctica was basically this primitive cratonic unit of the North American Craton and Siberia. And so Arctica kind of constituted this supercontinent, if you will. And keep in mind that supercontinents very early on in Earth's history may have been smaller than today because there wasn't as much continental crust available at the time. Maybe about 60 to 70% of the continental crust that we have today was around back in the Archean, so a little bit less. This is Arctica, I believe. Andrew, that's what you mentioned? It was a private message there. Oh, I see what you mean, the origin. So it's right here, the Trans-Hudson. So the origin that welded together Arctica was the Trans-Hudson origin. And we can see that right through here. So recognize what origins are, remember, right? Origins are mountain belts. What do mountain belts represent? They represent continental convergence. They represent convergent boundary settings and continental collision, accretion, right? That sort of idea. When you hear orogenesis, you should always think convergence, okay? Same with accretion, right? Think convergence. And so bringing all of these units together, we'd expect to see origins between the convergence of these units, right? Because these continental fragments are smashing together, essentially. And so this is where roughly the Trans-Hudson origin passed through. And how do we know that it's an origin? How do we know that there was an origin here? Now, this is 2.5 billion years old, mind you, right? 2 to 2.5 billion years old. So the mountains that were in this area are long gone. But what evidence is left over for the presence of mountain ranges that were once in this area in the rock record? What might be there? What would we expect the rocks to do? Exactly, fault. They will certainly erode later, but in erosion, that material is removed, right? So what can we see today that gives us evidence that there was a compressive, highly compressive environment and a mountain belt there? Faulting, for sure, that can point to it. And folding and metamorphic rock formation, exactly, guys, right? So high-grade metamorphic rocks, very strongly deformed rocks, right? And faulting structures as well, of course. And that's exactly what we see in these areas. So if we take a look at northern Saskatchewan, northern Manitoba, where this Trans-Hudson origin passed through, or was present, 2.5 billion years ago, and we take a look at the bedrock that's exposed there today, we see something that looks like this. Now, this is a sedimentary rock. This was a sedimentary rock called a conglomerate. So we can see clasts of sediment still stuck in there, right? A poorly sorted sedimentary rock. And what this black unit represents is a mafic sill, a basaltic sill, concordant with those sedimentary layers. It does not look like that today, right? It's very strongly deformed, very strongly metamorphosed. And this is what we'd expect in the heart of highly compressive environments like orogens, like mountain belt formations, right? The pressure is very high, the temperature is very high in the heart of these mountain belts, and the compressive stresses are very high. And so we're warping, we're metamorphosing these rocks. And so this is evidence of the presence of that trans-Hudson origin, which is the orogenic event responsible for amalgamating Arctica. And so remember to follow along with your table, right? Stage 1, supercontinent, Arctica. Time span of formation, about 2 to 2.5 billion years ago. The orogenic event responsible for amalgamating it, the trans-Hudson origin, the THO. Okay, so you can fill these in as you go. Now, we see associated with the trans-Hudson origin, and in these rocks that are strongly deformed, we see intrusions as well, granitic intrusions. How are these intrusions generated? Now, with respect to convergent boundary settings, how are intrusions of rock generated? How are intrusions of molten rock generated? That later will like solidify to form solid igneous rock, of course. But what process is at work here? How are we generating magma? Yeah, heat and pressure for sure, but more specifically, in convergent boundary settings, you guys know it. I'm just tricking you. Bingo, exactly. Flux-induced melting, hydration melting. This is a convergent setting. Right before continental fragments collide to form an origin, we have subduction of oceanic crust. In the subduction of that oceanic crust, we can generate magmas via flux-induced melting. Those magmas can ascend to the surface and intrude that continental crustal material above, right, forming a continental volcanic arc. And so these large bodies of igneous rock, called batholiths or plutons, are direct evidence for convergence, are direct evidence for oceanic slab subduction and therefore continental convergence, because they form in this manner. This is why we see them here in Nova Scotia, right? In Nova Scotia, we see large bodies of igneous rock, of granitic igneous rock. The South Mountain batholith, for instance, around Peggy's Cove, right? That's a large body of granitic igneous rock. That didn't start its life at the surface. That started its life 10 kilometers below the surface as a magma chamber. That magma chamber would have been feeding volcanoes at the surface that were once in Nova Scotia, but all of that volcanic activity has been lost to erosion. So that 10 kilometers of rock above our heads is gone. But we do see the remnants of that volcanism in the form of these solidified igneous bodies. The only way we can get that is through this process right here, through the generation of magmas, through flux-induced melting of hydrated oceanic slabs. And so the fact that we see these in Nova Scotia suggested that Nova Scotia was once right at an active tectonic boundary, an active subduction zone. This makes sense, right? The closure of the Iapetus and formation of Pangea and the accretion of those terrains on the margin of Laurentia, North America, saw the formation of the North America we know today, right? So this is why they're there. And this is why we also see them in any orogenic belt, like the trans-Hudson origin. So to really tie my point home, I want to show you one thing. A little video here. Let's close this, keep these. So I want to show you this little video, and I'll post the link to this in the chat. It's a little bit long. It's 6.5 minutes long, and it goes through from the Cambrian to present day and the evolution of plate tectonics. But I want to show you something in particular. So let's cue that video up. Okay, so this is Cambrian. Now we're going to flip through a little bit because the South Mountain batholith in Nova Scotia is of Devonian age. So let's flip to the Devonian and take a look at what was happening. Okay, so here's the Devonian. So the body of a granitic rock in Nova Scotia, this batholith, is from the Devonian. So we'd expect then in the Devonian, there is an active subduction zone off the coast of Nova Scotia. So let's take a peek here. This is exactly what we're observing right now. See this unit right here? Well, ocean. This is the Iapetus Ocean. This Iapetus Ocean is closing in this view, and it's only closing via subduction of oceanic crust, right? This is the nature of ocean closure. We have to subduct that oceanic crust. Therefore, Nova Scotia, being right about here in this view, is an active tectonic boundary, generating that magmatic activity. So in this view, you see the Iapetus close, continue to close, continue to close, and this is giving rise to a continental volcanic arc in the Nova Scotia area and along the eastern coast. Now we see the Iapetus fully closed, Pangea start to take shape. Now this is Pangea forming, and you can see Nova Scotia here, right here, and in the Carboniferous, when we find the production of vast coal beds, Nova Scotia is very close to the equator. So you can see in this view here, in the late Carboniferous, Nova Scotia is essentially right at the equator. And so ever since the Carboniferous, Nova Scotia has been moving northwards, essentially, to the position it is today. But I wanted to show you this quickly. We're going to come back to a couple videos, but I wanted to show you this one quickly to exemplify the formation of continental volcanic arcs through ocean closure, and then the eventual continental convergence forming orogenic belts. And once we get continental convergence, do we have continued substantial active magmatism and volcanism? Yes or no? For a bit, potentially, but remember the necessity that we need, right? We need subducting hydrated oceanic crust to generate magma, which can rise to the surface, giving rise to volcanism, right? So until that source of subducting oceanic crust is cut off, we have magmatism. But once we have continent-continent collision, there's no more oceanic crust to subduct. And so volcanism stops, which is why we don't see volcanic activity in the Himalayas, right? We see seismic activity for sure, but no volcanic activity because there's no oceanic crust there to subduct. Okay, right on. So, transitioning into stage 2 then, Arctica forms, and again, right, with these Wilson cycles, the supercontinent breaks up again, Arctica breaks up, and a new supercontinent, Nuna, forms at about 1.8 billion years old. Now, keep in mind, we're working in the very distant geologic past. So these dates are approximate. Right, we don't know exactly what was happening back then. We don't know exactly what the tectonic architecture looked like and how plates were moving specifically, right? So this is our best interpretation based on the evidence that we have preserved in the rock record. So stage 2 is the formation of a supercontinent that we call Nuna, sometimes referred to as Nina or Columbia, from other sources, but the majority of researchers, tectonic researchers, refer to this as Nuna. And so we're right about here now in the Proterozoic eon. Oops, sorry, right about there in the Proterozoic. And so again, you can fill this into your table, right? Stage 2, supercontinent, Nuna, time about 1.8 billion. The orogenic event responsible for the amalgamation of this supercontinent, Nuna, was what we call the Panochian orogeny. Not Pinocchio, Panochian down here. So this Panochian orogeny is, like the other orogens, exposed here in Canada. Now this is obviously eroded down. This is penoplaned as well, like the Trans-Hudson orogen as well. And we see exposure of these deformed rocks associated with the Panochian in the area of Sudbury, for instance. You can see them just kind of extending up into the Superior province in the Sudbury area, and then kind of extending down through Lake Superior and into the United States and into the southern United States and Mexico down in here. And so this was the orogenic event responsible for the amalgamation of Nuna. And now keep in mind, we're talking about North America specifically, right? There's other origins around as well, but the origin that's preserved here in North America is what we call the Panochian orogeny. And this represented the convergence of Arctica with a smaller Cratonic unit. And this is what's called the Yavapai or the Mazatzal origins. So these units kind of collided with Arctica, forming these origins in kind of the mid-United States, transitioning up into Canada a little bit in the Sudbury area, kind of mid-Ontario area. Just like the THO, just like the Trans-Hudson origin, this would have also been a very demanding mountain range, Himalayan-esque sort of mountain range. But like the THO, this would also be penoplaned and erode. Now, that material doesn't necessarily just get erased to the rock record, right? If we peneplane mountains by eroding and removing material, that material will go somewhere, right? Keep in mind, this is material shed from continental erosion. So the sediment is also felsic on average. The sediment is continental material. So it doesn't want to subduct, remember, right? And so sometimes it will enter the oceans just to be accreted into an accretionary wedge, or sometimes it will stay on the continents and accumulate in basins. And this is what we see in northern Saskatchewan, for instance, and I'll show you an example in just a moment. So this is what Nuna is theorized to look like. Here is our, I mean, there's several different reconstructions, some a little more detailed than others, but this is the Laurentia unit of it here. So this is the North American section. So you can see that there's likely other origins that are forming, right? Probably origins here, you know, origins here, wherever these continental fragments are colliding, we're going to form an origin. But in Nova Scotia specifically, we have the Panochian. And so as the Nuna supercontinent was forming, the Trans-Hudson origin was still eroding. It was still being penoplaned. And so sediments are continually being shed from the Trans-Hudson origin and the Panochian origin. And those sediments are being mobilized from topographic highs to topographic lows towards basins, right? Wherever that basin may be, a shallow sea, maybe intracratonic basins, right? Shallow areas on the continental craton themselves. Wherever a topographic low exists is where sediment will accumulate. The sediment being shed from this very ancient Trans-Hudson origin accumulates into these Paleoproterozoic origins. So the Trans-Hudson was formed in the Archean, and then the next eon is the Proterozoic. And so these Proterozoic basins start to form by erosion of these older mountain ranges. And those basins include the Theon Basin up here in Nunavut and the Athabasca Basin right here in northern Saskatchewan. So these basins represent the accumulation of sediment being shed from the Trans-Hudson origin. Now, the importance of the Athabasca Basin in particular, that I just wanted to mention quickly, is that it hosts the world's largest, highest grade uranium deposit right here in Canada in northern Saskatchewan. And as a matter of fact, one of the faculty members here in the Department of Geology, Erin Adlaka, did her PhD work on the uranium mineralization in this area. And so this is these are some figures from Dr. Adlaka's work, and you can see that uranium in the form of these kind of opaque uraninite crystals, which is uranium oxide, constitute a very, very high-grade uranium source. And so Canada is very well endowed when it comes to radioactive elements such as uranium. Okay, now I think we've already alluded to this a little bit in passing. Back when we were talking about plate tectonics, we were talking about the formation of supercontinents. One of the supercontinents that we mentioned was Rodinia, and this is the supercontinent that predates Pangea. So we've seen the formation of two, right? So keep in mind that the rifting and formation of supercontinents constitute Wilson cycles. Okay, always keep that in the back of your mind. So far we've seen 2 Wilson cycles complete. The formation of Arctica and the formation of, I almost started with my middle finger there first, formation of Arctica, then the formation of Nuna, right? So 2 complete Wilson cycles. Now the third results in the rifting of Nuna, of course, the rifting of that supercontinent, and the formation of a new supercontinent called Rodinia. Again, when we form supercontinents, this results from convergence, right? Continental fragment convergence, Cratonic convergence. Therefore, we'd expect to see origins, right? Exactly what we've been talking about this whole time. And so we'd expect to have an origin associated with the formation of Rodinia as well, exposed here in Canada. And we do. And this is what's called the Grenville origin, or the Grenville orogeny, if we're talking about the mountain forming event itself. Now, the assembly of Rodinia was approximately completed about 1.3 to 1 billion years ago or so, and started rifting and breaking up about 600 million years, so 0.6 billion years or so. Keep in mind, these are a little bit loose and fast, right? We don't have an exact, I mean, these are slow geological time processes, right? So it's our best guess. And so it started splitting up, Rodinia started splitting up right about here in the geological timescale, but life, complex multicellular organisms started to develop shortly after. So as Rodinia was kind of in the throes of rifting apart in the middle of a Wilson cycle, this is when we started seeing the first multicellular complex organisms come on the scene. And the very first, the best exposure in the world of these very first marine multicellular organisms are exposed right here in Canada, in Newfoundland, at Mistaken Point, right down the road from St. John's, basically. This is a UNESCO World Heritage Site. You have to actually take off your shoes and wear booties to walk along this rock. This is how protected this site is, because it hosts the very first multicellular organisms that are fossilized, mind you, that we have evidence of. Now, there was life before that, of course, monocellular life, but this is where we started really seeing the explosion of multicellular life during the kind of rifting of Rodinia. So there wouldn't be complex multicellular organisms during the formation of Arctica or Nuna, right? Multicellular organisms would not exist. So if you went back in time and were standing on Arctica, well, you would most likely suffocate because the atmosphere wouldn't be suitable for you. Same with Nuna, but you wouldn't see anything. You wouldn't see trees, you wouldn't see moss, you wouldn't see lichen, you would see nothing. It would essentially be rock and water, and that's essentially what you would be seeing. And maybe some very, very primitive microorganisms in that water. And so now we're here, the formation of the Grenville origin, which is very, very beautifully exposed in the Algonquin Park, Muskoka region of Ontario and up into Quebec. Now, along Georgian Bay, Hudson Bay, we see these really, really nicely exposed high-grade metamorphic rocks associated with Grenville. So Toronto, we don't see too much of that because Toronto has is overlain. Those ancient rocks associated with the Grenville are overlain by younger sedimentary sequences. So it's not too well exposed in the Toronto area. But as we go northwards, the sedimentary cover thins and basically is absent. And so we get to see those really deformed basement rocks associated with Grenville. So remember that piece of evidence, right? These high-grade metamorphic rocks, strongly deformed rocks, are always evidence of these, very, very compressive, deformational situations, such as orogenic events. So stage 3 is the formation of the Rodinia supercontinent, which was complete about 1.2, 1.3 to 1 billion years or so. Now, during the closure of these oceans, again, right, we expect to see the formation of continental volcanic arcs, right, just like we see here in Nova Scotia associated with the formation of Pangea. So likewise, we see this evidence as well, evidence of volcanism, the accretion of volcanic island arcs, the accretion of microcontinents. This is all what went into forming Rodinia, just like we see in Pangea. And so here is an artist's reconstruction of Rodinia. We often see this kind of crescent shape expressed. I'll show you where that comes from in a video in just a few moments. Here is another reconstruction, and we see Laurentia, so Paleo North America here, and we see the Grenville origin right through here. So Nova Scotia has not accreted onto North America yet. The eastern seaboard of Nova Scotia is not yet there. As a matter of fact, the terrains that now form modern day Ontario and parts of Quebec and parts of central United States were just accreting. So during the formation of Rodinia, this is when we kind of put Ontario, kind of southern Ontario, onto the flank, and some of Quebec onto the flank. This is when we accreted that material. So just to remind you, penaplanation of these mountains, right? In this area of Ontario, in the Muskokas of Ontario, we don't see demanding mountain ranges anymore, right? But just like the Trans-Hudson, just like the Pinokian, this would have been a very demanding mountain range, which is then eroded and penaplaned. Isostatic adjustment uplifts these very deep-rooted rocks, and we see these high-grade rocks at surface. And so in Ontario now, in this region, we see something that looks like this, right? Rather flat-lying, penaplaned land. So if we go back here, Hannah had a question, Baltica accreting, forming part of the orogeny. Yes, so Baltica is the area of kind of Northern Europe. This is what they called Baltica back during this period in time. So Baltica would be a fragment that constitutes essentially Europe, mostly Northern Europe, that was also smudged up against North America at this point in time as well. So again, where's that evidence come from? Well, the rock record, right? The structure of the rocks and the fabric of the rocks, such as these very, very high-grade metamorphic rocks. These are pictures that I took myself when I was driving south from Sudbury. So I was driving from Sudbury and I went down the Georgian Bay coast towards Parry Sound. And along Parry Sound, we see these road cuts. So the highway is just behind me in this image. You can see the drill holes that they did the road cut through. And so it beautifully exposes this high-grade metamorphic rock. We take a closer look at that, you can see that this rock is gneiss, and we haven't discussed gneiss in this course in detail because it is a topic for Geology 1200, but it is a very high-grade metamorphic rock, and we generate these rocks in the roots of mountains. In fact, here's a piece of that rock right here. So this is high-grade metamorphic rock that I collected from this exact outcrop, which is about 1.2 to 1 billion years old, which resulted from the amalgamation of Rodinia. So I'm basically holding a piece of the Grenville origin in my hands here, resulting from the formation of Rodinia about 1 billion years ago or so. Once you kind of get an appreciation and understanding for what these rocks actually represent, looking at them and holding them becomes a little bit more, I don't want to say spiritual, but like significant. You know what I mean? Like holding that rock of that age with that significance. Question 2, Hannah, another private message here. Question 2 is related to the evidence that we use to locate origins, or the evidence of origins. And this comes in the form of very highly deformed rocks, like high-grade metamorphic rocks that are very highly deformed, right? Which represents the heart of orogenic belts. So we see these rocks. This is what, you know, the characteristic coastline of Georgian Bay in Ontario looks like. Very, very high grade, very highly deformed metamorphic rocks, which represent the crustal roots of that Grenville origin. Now, just like we saw the sediments and peniplanation of the Trans-Hudson origin yielding the basins, the Athabasca and the Thelon Basin, right? The sediment was being shed and mobilized into this basinal environment. We see the exact same thing happening here with the Grenville. So the sediments that were being shed from the Grenville origin during their erosion between 1.2 to 700 million years ago or so. So the Grenville origin would be, right here. And those sediments were being mobilized away from that origin, right, through rivers and streams. Those sediments found their home in this Mackenzie Mountain Basin. So back when these sediments were accumulating in this environment, it was a basinal environment. It was a low-lying, topographically low area where sediments could accumulate. However, if we take a look at the Mackenzie Mountains today, or this area, it looks like this. It's no longer a basin, right? So these layers that you see in the sedimentary rocks here, so these are sedimentary layers that you see here. Those are the sedimentary layers that were deposited in a basin through the erosion of the Grenville Mountains. Now, the law of original horizontality and the law of superposition applies here. These would have been low-lying, of course, right? We can't put sediments up onto the top of a mountain like that and lithify them there. This would have been a basinal environment, like a shallow marine environment. Now, they're in a mountain today because of, a billion years of tectonic influence. They've been upthrust into this mountain through later tectonic forces. But those sediments that we see right there in the Mackenzie Mountains represent sediments shed from the erosion of those Grenville Mountains, from the Grenville origin. Now, what's really neat about this environment is in these basins, like a marine environment, we'd expect to have life, right? These are very productive environments for life. Now, keep in mind, this is about 1 billion years ago or so, so we still don't have complex life, but there was monocellular organisms existing. And maybe even the first primitive multicellular organisms. This is a fossil from those mountains. So some of the rock units in these Mackenzie Mountains host fossilized organisms such as this little guy. This little guy is a multicellular organism of eukaryotic cells. And now eukaryotic cells are important because they're sex cells. They are cells that reproduce sexually. Therefore, Canada has the earliest direct evidence of sex. Right here in Canada, in the Mackenzie Mountains, the presence of eukaryotic cells. So we can be quite proud of that as Canadian geoscientists. It's a very, very small specimen though. This is only about 200 microns long, about 0.2 millimeters long. Very small, but still multicellular and eukaryotic. This is another fossilized organisms from those Mackenzie Mountains, and this is the earliest known example of biomineralization in a eukaryotic system. So this is the first example of eukaryotic cells exploiting biomineralization to build their skeletons through the mineralization of silica or carbonate, just like oysters or mussels would do today. So evidence of the first microscopic organisms, the first monocellular organisms, is much, much older than this. This is about 1 billion years or so, however, right? But they're eukaryotic, and that's what's important. Now, prokaryotes, even before then, proterozoa rather, would be much older, very primitive, 3.5, roughly 3.5 billion years ago or so is when they kind of got their foothold, kind of got their start. There is a paper that was published in Nature about the earliest evidence of some of these organisms that are thought to have formed around hydrothermal deep sea vents like black smokers. Now, I believe there's a little bit of contention around this paper. It's not 100% certain whether or not this is a true fossilized form of microscopic life, but it was you know, a substantial finding nonetheless, which is why it's published in Nature, a very high impact scientific journal. But I'm going to show you a little video of that just to kind of give you an idea of what these researchers were doing. Okay. Okay, everyone can see my YouTube screen? Okay, excellent, and away we go.
We have discovered microfossils that are composed of hematite. Basically, it's iron oxide, it's like rust.
Through laser imaging of the samples, we were able to identify the microfossils as the oldest one.
This is a slab that's been polished. There are these structures here. It is cut on the right-hand side, but you can see kind of a structure that bends the layering in this rock. And it is within these features in part that we find the microfossils.
In diameter, the microfossils half the width of a human hair. They can be anything up to 0.5 millimeter.
The microfossils we discovered are about 300 million years older than the previously thought oldest microfossils. These rocks have a minimum age of 3.77 billion years, but some scientists in the field consider them to be as old as 4.28 billion years. So they are within a few hundred million years from within the accretion of the solar system and of planet Earth and the sun and the moon and so on. These rocks are being mostly composed of silica and hematite, this iron rust. We find these kinds of environments today.
There's a black smoker, hydrothermal vents,
either in the deep ocean and in some places not in so deep localities that exhale a lot of iron particulates in water. And this is thought to be the material that these bacteria actually eat and breathe. The rocks are located in the province of Quebec on the shoreline near to the Mastapoca Islands. When I saw these structures in the field, I said, I have to sample this.
One of the big questions when it comes to early life studies is whether or not the organic carbon we find in these rocks is actually biological in origin, especially in hydrothermal vent environments where you can have special reactions called the Fischer-Tropsch reaction.
We used a very robust, rigorous approach to test whether these microfossils we discovered were non-biological structures.
And we were able to do this with our laser imaging system by looking at the minerals the organic material was associated with. And we find it with these key minerals, apatite and carbonate.
If we are right with our new model for the origin of these spheroidal structures in these rocks that contain.
So the importance of apatite and carbonate is that carbonate contains carbon and oxygen. Apatite is a phosphate mineral. There's phosphorus in living organisms, right, in DNA and RNA. And so the presence of now minerals associated with this containing phosphorus and carbon might be evidence that it was once life. You know, obviously we're not preserving these ancient organic molecules because they've been exposed to very high temperatures and pressures since in that 3.7 billion years of their history. And so they alter, they convert, they can break down, but they might not actually leave the system. They might just change form into a new mineral, an inorganic mineral in this case.
In these fossils, then we might want to look for these kinds of things on other ancient planetary surfaces.
Rills on Mars, evidence of water.
I'm keen to look at more examples of hydrothermal vent deposits, and if we can take our knowledge of how organic matter and microfossils are preserved on Earth and apply them to hydrothermal systems on other planets like Mars or Europa.
In 2007, there was one of the Martian exploration rover found beds of hematite concretions. They were called blueberries at the time, and it made a big news splash as well. The origin of these structures is not fully understood, even on Earth where we find them. but we don't know really how organic matter can potentially be involved in making these structures.
The most exciting thing about this discovery is that we know that life managed to get a grip and start on Earth at such an early time in Earth's evolution, which gives us exciting questions as to whether we are alone in the solar system or in the universe. If life happened so quickly on Earth, then do we expect it to be a simple process and start on other planets, or was Earth really just a special case?
Okay, well, if you guys are interested in taking a peek at the picture and some of the images that they published, you can find it in that Nature article there. You should have access to that through this new library. But they mentioned one thing in there, the Fischer-Tropsch reaction. This is actually something that I also study in my work with hydrothermal fluid systems. To give you a little insight on that reaction, the Fischer-Tropsch reaction is a reaction that consumes carbon monoxide or carbon dioxide in the presence of hydrogen gas and transforms it into methane or higher order hydrocarbons like ethane, propane, butane. Now, this is completely inorganic. We can generate methane and higher order hydrocarbons in an abiogenic inorganic fashion, without life being present there. So this is the question, right? Were these hydrocarbons that they're finding, these organic species, were they generated through an abiogenic mechanism? Or is it more of a top-down approach? Was biology there generating these organic molecules, and then those molecules broke down to form lighter molecules like, you know, hexane and pentane and more complex branched hydrocarbon molecules? Yeah, and so I want to also show you this while we're here. This is a little animation, quick animation here showing Rodinia specifically. So the formation of and breakup of Rodinia. Let's get it going here. Okay, so now we're forming Rodinia. Here's the supercontinent Rodinia starting to take shape. Remember, about 1.3 to 1 billion years ago, it kind of really gets its true form. And so we kind of see that crescent shape begin forming here. And we'll start seeing it kind of break apart at about, the 600 million mark. We'll start seeing it kind of rift again. So we're kind of floating around in Rodinia here. Rodinia is not static, of course. Plate tectonics are always moving, so it's always kind of changing shape and form, but it's a supercontinent nonetheless, right? So this is Rodinia. So now we can really see that crescent shape begin to take form here. And, it's starting to kind of rift apart a little bit here, starting to break up. This is one of the main projections people use for Rodinia, this large crescent sort of shape. But at this point in time, Rodinia was in the process of continental rifting. As you can see, here goes Laurentia. So there's North America moving northwards, forming the Iapetus Ocean in between. There's Baltica down here. So you can see Scandinavia over here. So here's Baltica, here's North America, Laurentia. Here comes some of the eastern Canada, right? So there we go, accreted some of the eastern Canadian terrains, and here is the Iapetus, which in this small area is referred to often as the Rheic, same idea. And so now we're going to be closing up this ocean here when we start forming Pangea. Okay. What was question 5 in the ice? I just want to make sure I'm getting to that. Yes, okay, here we go. the modern example of a continental rift system. So in theory, we could have answered this a long, long time ago. What's a good modern example of a continental rift today? You guys remember? Bingo, East Africa, right? So the East African rift system, that's a perfect analog to continental rifting today. That is basically the very earliest form of continental rifting. That's what it looks like in East Africa. And eventually that will evolve into a shallow seaway there, kind of rifting apart West Africa from East Africa. And so that brings us to continental rifting, right? Because after the creation of a supercontinent to complete the Wilson cycle, or to move through the Wilson cycle, we rift this material apart again. And so using Japan as a sort of example of what back arc extension is. So Japan is a volcanic island arc, and behind Japan, in the Sea of Japan, this is what we call a back arc, right? Remember, forearc and back arc, right? What's before the volcanic arc and what's behind the volcanic arc. So the Sea of Japan is a back arc basin, exactly. And in these back arc environments, we often see extension. So tensional stress, kind of pulling that basin apart a little bit. It may be a little bit counterintuitive, but we have compression right at the subduction zone environment. But behind the arc, there can be some extension. And you can see this in terms of heat flux. So in your subduction lab that you guys did, I think a week or two ago, you saw heat flux measurements, right? You were plotting the heat flux with respect to the Japanese trench. And you found that when you're closer to the trench, there's lower heat flux, right? It's compressive, everything is locked together. But as you moved into that back arc environment of Japan, you saw the heat flux measurements go up, relatively speaking, right? This is because this is an extensional environment. The crust is thinning a little bit here, and so this allows heat to escape more readily through this thinner crust. And so this is an example of a back arc extensional system. So imagine the Grenville orogeny being formed. Behind the Grenville orogeny, there's a back arc, right? Behind the formation of that orogeny or that continental volcanic arc, we can have a back arc situation. And so there can be some extension. And we see evidence that there was a back arc system here through the presence of this Kiwiwanan rift system right here. So some evidence of that. Oh, sorry, there's a bit of an, oh, I see. I haven't activated this yet. Okay, there we go. So here's the Kiwiwanan rift system. There was evidence of that here. So this was a continental rifting environment that actually stopped. It died out. It didn't complete its rifting, just like the Bay of Fundy, right? We see evidence of rifting in the Bay of Fundy. We see lava flows in North Nova Scotia. And so this is resulting from the rifting in the Bay of Fundy. However, that stopped because rifting in that environment quieted down, that went extinct, and then rifting continued, continental rifting continued off the coast of Nova Scotia, where the modern day divergent boundary is in the Atlantic Ocean. If the Bay of Fundy rift continued, well, Nova Scotia would probably be in West Africa today, as a matter of fact. I'm not quite sure about Europe with respect to the Rhine Valley and what their continental rifting situation looked like, but potentially. Maybe. So evidence of rifting, how do we know that this was actually a failed rift? Well, if we just look at our analog in Nova Scotia, we find evidence in the form of lava flows, right? These lava flows that are overlying Rift Valley sediments. We see the same sort of evidence in this area of North America as well. We see mafic intrusions like sills and dikes. We see rift valleys that are now basins that can accumulate rift valley sediment, and horst and graben structures, right? This is a perfect structural piece of evidence for the presence of an extensional boundary or an extensional situation, right? We'd expect to see horst and graben structures, which are interconnected normal faults resulting from extensional stress. Here's one piece of evidence there. So we see these Rift Valley sediments, these reddish Rift Valley sediments here, and we see these lava flows. So this is actually a sill, not a flow, to be specific. So remember what sills are, right? They're these planar intrusions that are concordant, parallel with sedimentary layers, sedimentary layering. And so that's a piece of evidence that there must have been some volcanic rifting activity there, right? If we're rifting, we're forming new oceanic crust at these divergent boundaries, right? Through decompressional melting. Decompressional melting yields mafic material, like at divergent plate boundaries, oceanic crust. So this is a piece of evidence for that. Can you think of a modern analog? Well, we've already said it. East Africa is a great example. And so we see this kind of non-linear continental rift system starting up here in Ethiopia and Eritrea and extending down into Namibia, or sorry, not Namibia, Kenya. So now we're breaking up Rodinia. We have the Iapetus Ocean forming. So this is basically the completion of stage 3, right? Stage 3 was Rodinia, and so now we're breaking up Rodinia. We're starting to go mid-Wilson cycle again here, starting to form the Iapetus Ocean, which kind of represents a Paleo-Atlantic. You can kind of think of it as the predecessor for the Atlantic, and you can kind of see the predecessor for the Pacific forming as well, which we call the Panthalassic, an enormous ocean that would have encompassed essentially the entirety of the globe other than this collection of continental material on one side. So it's kind of like our ancestral Pacific, if you will. Nova Scotia has not accreted yet, mind you, right? Because we're still diverging the Iapetus Ocean, and so it hasn't accreted yet. But in the red circle is where Southern Ontario is. So this is basically Ontario right there, Southern Ontario. And so in this view, about 750 million years ago or so, Southern Ontario was a coastline, was a passive margin environment, much like Nova Scotia is today, a passive margin environment. So we'd expect to see evidence of this passive margin environment in Ontario preserved in the rock record, right? And indeed we do. And we're going to come back to that next lecture as evidence that basically the passive margin of Laurentia was right around here in Southern Ontario and the St. Lawrence River Valley. So we'll stop here. We only have a handful more slides left in this lecture, and then what we're going to do is transition into stage 4 and 5 next week, with emphasis on stage 4, which is the formation of Pangea and the eastern North America. So the maritime provinces, Atlantic Canada provinces in particular. All right. So far, so good, everyone? I have a question here from Hannah regarding Gondwana. So what in particular did you have a question about, Hannah, regarding Gondwana? And to answer Sarai's question, the spelling for question 2, well, I won't give you the exact wording, but the evidence comes in the form of deformation, right, in the rock record. Remember what our evidence is, right? Our evidence comes from the rock record. And so the composition, the fabric, the structure of those rocks, how do we express that to take, oh my God, I can't speak today. How do we expect that to look in the heart of an orogenic system? Well, we expect it to be very high-grade metamorphic rocks and very highly deformed rocks, right? That's evidence of the heart of an orogen, right? Because orogenic events are very highly compressive, so we'd expect to see very deformed rocks resulting from that. Yes, Hannah, exactly. Gondwana is not, I don't want to say supercontinent, but it is a continental fragment. You can kind of think of Laurentia as ancestral North America. Think of Gondwana as ancestral Africa, or often called Gondwana land is ancestral Africa. Baltica, you can think of as ancestral Europe. And so they were given slightly different names. And so in that view, in this view, the sediments that will eventually form the Magma terrain in Nova Scotia are still being formed. They're still being deposited, as a matter of fact, on Gondwana. So right around here. There's the passive margin sediments off the coast of Gondwana that will eventually go on to be the terrains we see right here in Nova Scotia, the Magma terrain. So Nova Scotia represents passive margin sediment accumulating off the coast of Gondwana. So the Nova Scotian Magma terrain is African sediment that has now been lithified into sedimentary rocks and metamorphosed via the Appalachian orogeny. Good question. Any other questions, guys? Today? Okay. Let me just pull the chat up here. All right. Okay, so I flipped back just a few slides from where we left off because I just wanted to remind you of the supercontinent Rodinia, which is basically the supercontinent that predates Pangea, that split up, generated the Paleo-Atlantic, if you will, which we call the Iapetus Ocean, and then the reconvergence of these continental fragments is what generated Pangea to complete that Wilson cycle. And now we're kind of in the middle of a new Wilson cycle with ocean basin still developing. So the Atlantic Ocean is still spreading. The west coast of Africa and the east coast of North America and South America are passive margins. And so they're accumulating sediment as the ocean basin grows in between. Now, eventually something will happen. The tectonic architecture of the Atlantic will change and a subduction zone will generate. Now, this is theorized to probably zipper up the east coast of North America. So currently there's a subduction zone in the Caribbean, and this is what gives rise to the Lesser Antilles Islands, such as Grenada and St. Lucia. All of these islands in the Lesser Antilles are volcanic islands. They're volcanically active because there's a very small subduction zone there linking the Atlantic plate to the Caribbean plate. So it's a very small example of ocean-ocean subduction generating a volcanic island arc, which are the Lesser Antilles Islands in the Caribbean. Now, it's theorized that when the architecture of the Atlantic flips and the Wilson cycle kind of starts coming full circle and we start to converge and close the Atlantic Ocean, this is where the subduction zone may start. So it may kind of zipper up the east coast of North America and generate a subduction zone there. And so the beginning stages of Atlantic Ocean closure may actually begin with the generation of an active margin on the United States and Canada's east coast. But this will be, you know, many, many millions of years in the future, of course. And so just to remind you of this view here, in this view, we discussed we discussed the paleo coast of Ontario. And so in this view, before Pangea was constructed, the southernmost portion of Ontario and Quebec was a passive margin. There was shallow sea infiltration here as well. So this was a productive area for the generation of reefs, for the accumulation of sediments, as we can see down here. So everything in northern Ontario represents the Superior Province, right? Very, very old Canadian shield cratonic rocks. And now just south of that, this is still cratonic material just overlain by platformal rocks now. And so remember those words, right? Craton can be overlain by platform rocks, which are basically sedimentary cover, essentially. And so in this case of Southern Ontario, we see direct evidence for that passive margin environment that was persisting here during the development of the Iapetus Ocean as Rodinia was breaking up. And we see that in the form of sedimentary rocks that are overlying those high-grade metamorphic cratonic basement rocks. So in this view here off of the 401, near 1,000 islands. So as you're driving from, say, Ontario, say Toronto to Montreal, you'll pass by this outcrop or very close to it. And you'll see these sandstone layers overlying Precambrian basement rocks. So very, very old Cratonic rocks, Precambrian rocks, overlain by much younger sedimentary platform rocks. And during the convergence of Pangea, and shortly after the convergence of Pangea, this area was infiltrated by shallow seas. And so during this period in time, primarily the Silurian to the Devonian in the Phanerozoic now, not Precambrian anymore. So during this time, these shallow seas were perfect environments for the formation of limestone reefs, as we see in shallow seas, for instance, the Caribbean, right? The formation of reef environments, which is limestone. And so this limestone and dolostone is what kind of dominates the southern Ontario landscape now in the form of the Niagara Escarpment, which it represents one flank of that Maritimes Basin. So here's the Michigan Basin. So here's the Michigan Basin right here. And if we were to look on angle, so if I were to cut a transect through the Michigan Basin and look at its side, it would look like a basin, right? With sedimentary infill, and let's say that's the surface now. It would look something like this, right? Because that sediment was accumulating in sort of a topographic low, a gravitational low, a basin, in other words. And so it's kind of like a large synclinal structure when looked at side on. So if I was standing over here, I would see the exact same rocks outcropping in this area of Ontario, for instance, right here, as I would over here in this area of Michigan. The same rocks would be visible because it's this very, very broad basinal, synclinal sort of structure. And this is what we see in the bottom left image, is one of these outcropping units, which in this case is called dolostone. So there's that video we watched last week. Okay, and so today we're going to talk about now the convergence and amalgamation of the supercontinent Pangea, which gave rise to the Appalachian Mountains and the accretion of the Atlantic Canadian terrains, such as the Magma terrain that at least I am standing on today in the Halifax area of Canada. And so this started to proceed at about the beginning of the Cambrian or so. This is when we started seeing the kind of that Wilson cycle come full circle and the closure of the Iapetus Ocean to begin generating Pangea. But remember, before we have any continent-continent collision, we have subduction and accretion. And so we're going to get into stage 4 today and continue into Wednesday, and we'll see how far we get with stage 5, which is the accretion of the western terrains in the Canadian Cordillera, so British Columbia and up into Alaska. Okay, so that was it. Just a few additional slides there for that one. I'll close that. And so here we are. Now, I'll tell you later. I was going to start with something, but I think it's more apt for later in the lecture. So this is a view of joggins, and I'm using this view right here to give you an example of the rock types that begin accumulating during the, that's why you guys were shaking your head, sorry. I was like, is it not joggins? Okay. How's that? Okay. So this is joggins, I believe. At least the website told me it was. No, it is. So this is joggins, and these sedimentary strata were accumulating, at least the sediment that you see here that are now sedimentary rocks, were accumulating during the Carboniferous. And during the Carboniferous, as we've mentioned, Nova Scotia was quite tropical, very productive. It was near the equator, and this is when Pangea was really finally starting to come together during that, late Carboniferous or so. So I figured that was a apt image. So now we're in stage 4, and you can start filling out that corresponding row in your table if you're following along using that table. Stage 4 now, we're talking about the supercontinent Pangea, and we're going to talk about a couple different origins that are all pretty much associated with the Appalachian origin. So that's the main origin that we're talking about here, right? The Appalachian. With the formation of every supercontinent, we see the formation of orogenic belts as well, right? Origins. In Canada, and the United States, so in North America, this origin is called the Appalachians. However, the exact same origin can be seen in Northern Africa, which are called the Atlas Mountains, and in the UK and even in South America as well. It's this kind of pan mountain range, this Pangean mountain range, if you will, that stretched across the entirety of Pangea. And now as those continents begin to rift apart and break up again, we're kind of left with our North American fragment over here, right? But we see the similar process occur across Pangea and Northern Africa and the UK and Scandinavia and even parts of Northern South America have remnants of that same origin. So the formation of Pangea really started commencing with the closure of the Iapetus about 480 million years ago or so, 500 million years ago or so, and it was essentially complete in the Carboniferous, so about 380 million years ago or so, which is pretty much the Devonian Carboniferous boundary in that region right there. Now, there are multiple collisional events that are associated with the formation of the Appalachian Mountains, just like the formation of any origin for that matter. This isn't one continuous mountain building stage, right? There are terrains that are accreted, and during the accretion of various terrains, there are, if you will, are different kind of suborogenic events, right? We have different punctuated stages of deformation with the accretion of one terrain after another, and then the final ocean basin closure and continent-continent collision. So orogeny is kind of a stepwise process. Sorry. Orogeny is a bit of a stepwise process that proceeds through continual accretion and then final continent-continent collision. And so keep in mind, it's not just one main collisional stage. It can kind of be broken up into pieces that are separated in time by many millions of years from one another. And so in Canada and in Nova Scotia in particular, we do see evidence of those kind of pulsed stages of orogenic formation. And so we can kind of break these into suborogenic events that we give names like the Alleghenian or the Acadian or the Neo-Acadian orogeny. But these are all umbrellaed under that main Appalachian or orogenic event associated with the closure of the Iapetus. And so just to put some things in time here, so here's the Phanerozoic. Now, in the Phanerozoic, this is when we see the closure of the Iapetus and formation of Pangea, remember. Just before the Phanerozoic, in the late Paleozoic, or sorry, late Proterozoic, this is when we see basically the beginning of the rifting of Rodinia. So, you know, just down in here, sort of thing, in the Precambrian, the very late Precambrian is when we see rifting of Rodinia. And so putting these things in time here, we see one right here, and this is related to the accretion of the Humber and the Dunnage terrains. So you can see that this orogenic event is spaced over many millions of years, and it's kind of going stepwise through the accretion of these terrains sequentially. So down here in the Ordovician, about 450 million years ago, is when we see the accretion of the Humber and the Dunnage terrains. We're going to talk about these terrains in a little more detail, mind you, but the Hummage terrain represents these passive margin sediments that are off the coast of Laurentia, as we're accreting the Dunnage zone or the Dunnage terrain, which represents volcanic island arc fragments, which are also accreting against Laurentia's margin. Now, if we hop ahead by a few tens of million years to the late Silurian down here in 2, So late Silurian, early Devonian is when we see the Gander and the Avalon terrains begin to accrete. So the Gander terrain is the passive margin sediments that are off the coast of the Avalon terrain, which represents a microcontinent, which is converging and accreting. Just like we saw this kind of microcontinental convergence when we were first forming Arctica, that very first supercontinent that we were talking about. Remember, we talked about the Slave and the Ray and the Hearn and the Superior microcontinental provinces that kind of accreted and amalgamated together. So it's the same idea here. The Avalon represents one of those microcontinental fragments. So you can see that we're assigning slightly different orogenic terms to these based on this kind of stepwise procedure, right? We got the Tectonic orogeny over here, and then the Akkadian orogeny, and then down here, during the Devonian and Carboniferous, the Alleghanian orogeny. So these basically just represent pulses of the Appalachian orogeny. Okay, so these are kind of just staged stepwise pulses under that main umbrella of continent-continent collision, which is proceeding and kind of culminates with the formation of those Pangean mountains, which we call the Appalachians. So in the late Devonian now, right about here, this is where we see the Iapetus Ocean fully close. So now the full breadth of Pangea is really starting to take shape. Gondwana and Laurentia have fully closed. So Africa, Northwest Africa, is essentially a butt with the Maritimes provinces, with Nova Scotia. The Magma terrain in particular in Nova Scotia represents the most outboard terrain, meaning that it's the last terrain to dock on the flank of Laurentia. It's the furthest outboard. And the Magma rocks represent passive margin sediments that were off the coast of Gondwana land at the time. So the sediments that we see in the rocks in Halifax. So if you're walking through Halifax or around St. Mary's, the rocks that you see on the Halifax Peninsula and in much of southern Nova Scotia represent passive margin sediments that accumulated off the coast of Paleo-Africa, off Gondwana land. And now, as we've seen, these accretionary events can smush those sediments up and lithify them and deform them into these, deformed meta-sedimentary rocks, which we see today in Magma. So the rocks that we have here in Nova Scotia actually represent African sediments that were shed off terrigenous African sediments that were shed off of Gondwana land and accumulated on that passive margin. The South Mountain batholith was emplaced right around here during the Devonian. So I mentioned that the formation of these large plutons and batholiths is evidence of magmatic activity, of course, right? And we can generate that magmatic activity via convergence through, for one, hydration melting. And now, perhaps you remember, perhaps you don't, that I kind of alluded to another process that can generate melts related to metamorphism, if it were. And so I mentioned that, we can take in high-grade metamorphic rocks, we can heat the rocks up sufficiently high to partially melt some of that material. Now, I don't want to get into this in too much detail, but I did want to show you that, there are lots more avenues that we haven't really explored here. We're kind of really just scratching the surface of magmatism, of deformation, of geological structure. But there are all sorts of rabbit holes that we can shoot down. Namely, just very briefly, and for your own interest, I'd like to show you this example of metamorphic rocks. So let me just stop this share real quick and flip to this one. And so I mentioned the presence of high-grade metamorphic rocks. These metamorphic rocks form in the heart of mountain belts, right? Very, very deep crustal units of rock that are under immense pressure and temperature. And so this rock represents a very high-grade metamorphic rock called a gneiss. Now, in these immense temperatures and pressures, these high-grade rocks have a tendency to kind of separate, compositionally separate layers. So we see these darker layers right here, which are more mafic minerals, minerals that contain more iron and magnesium. And we see these lighter, pale layers, which are more felsic layers, so that contain minerals that contain less iron and magnesium. Now, interestingly, these felsic layers, just like felsic rocks, melt at a lower temperature than these mafic layers, right? And we saw this when we were talking about partial melting of the mantle and melting of continental crust, right? Felsic material has a lower melting point than mafic material. So if I were to take this rock and melt some of it, if I were to melt just a little bit of it, the first material to melt in this rock would be this felsic material. And so this is where we enter this kind of fuzzy boundary between metamorphic rocks and igneous rocks. And this is a process that's called anatexis. Now, we're not going to get into the details of anatexis, but anatexis means the partial melting of a rock, the partial melting of the felsic material primarily in that rock, not necessarily related to heating by the mantle or hydration melting. So let's look at this rock. This is an even higher grade metamorphic rock. You can see that it's gneissic, but it's very deformed. This is an extremely high grade rock. You see this kind of little pool right here, this little cavity of felsic material. That represents a body of once melted felsic material. So in these rocks, we are partially melting just a little bit of this stuff. And sometimes it can squirt out of those rocks to form a new magma somewhere else, or a new magma chamber somewhere else, or a sill or a dike or something like that. Or that melt can re-solidify in situ to form now what was once a little puddle of partial melt that's now locked back into the rock. This is an extremely high-grade metamorphic rock called a migmatite. And migmatites show this process of anatexis, which represents partial melting of this felsic material from a rock. Now, I wanted to mention this because it uses a process that we've already discussed, decompressional melting. And now in decompressional melting, we've really only talked about it in context of divergent boundary settings, right? And kind of lowering the lithostatic load and partial melting some of the upper mantle to form mafic rock. Now, I didn't want to really get into this in too much detail, and I'm still, again, really only telling you this for interest's sake. But we can also get partial melting of crustal material in the exact same manner. So imagine you have an extremely thick pile of continental crustal material, right? An origin, for instance. And now we start unroofing that origin. I start eroding the material off of the top of those mountains very rapidly. And so in a rather geologically rapid fashion, I begin to isostatically adjust that origin because I'm unroofing it through erosion. Now, what happens to those extremely hot rocks in the deep origin? They can undergo decompression melting. And so as a matter of fact, those very deep rocks, which is continental crustal material, can undergo this same process of decompression melting and partial melting of the rock, anatexis. So we can generate vast quantities of this sort of material and squeeze it out of the rocks to form a magma chamber somewhere else. That's a more advanced geological aspect, but I wanted to show you that, decompressional melting is not just exclusively related to, mafic material at divergent boundary settings. But from what we talked about, at least, this is how we kind of scratch the surface with regards to melting characteristics. Any questions about that? I might have went off on another tangent there.
So the depth of the hot rocks at the center will be changing.
Right.
And does it have to be fast? Because as the depth increases, the temperature increases. So if it happens too slowly and the depth and temperature change in equivalent amounts, it wouldn't happen, right?
Exactly right. So the unroofing and isostatic adjustment has to be rapid enough to decompressively melt this material, because it's isothermal. Remember, we need to maintain that high temperature while removing pressure. And so that's exactly right. If the unroofing is too slow, then pressure and temperature both come down together, and we don't have a sufficient temperature. But in a rather isothermal adiabatic system, maintaining temperature as we unroof, then we can get those anatexites, those partial melts of continental crustal material. And so that's another way that we can produce these large magma chambers in the crust, analogous to South Mountain batholith material. So without confusing you too far and giving you too much information, the South Mountain batholith represents the partial melt of sedimentary crustal material at depth in a rather similar process to this. We see the formation of hydration melts and magmatism related to continental volcanic arcs also in the Maritimes in areas such as New Brunswick. Sugarloaf Mountain, for instance, is an example of one of these volcanic plugs related to hydration melting and volcanic arc production. But it's twofold. We can produce magmas in many ways. Okay, so I'm not going to ask you anything about that on the final or anything like that. Like, how can we produce magmas through, felsic magmas through decompressional melting? I won't ask you that, since we didn't really belabor that point. That's more of a point for Geology 1200. But I just wanted to tell you, just to let you know. Okay, so let's go through Atlantic Canada in a little bit more detail in terms of the accretion of the terrains that we're familiar with. So during the middle of the Wilson cycle, we had the development of the Iapetus Ocean, as we've mentioned. We can think of this like the precursor to the Atlantic. And so we have Laurasia over here, Laurentia, Paleo North America over on this side, North America, and Africa over on this side. And so you can see here a passive margin. Right? There's the passive margin off the coast of Africa, and this is where the sediments are accumulating that'll eventually accrete and lithify to form the Magma rocks that we're standing on today. And so that's where they got their start, right there off the coast of Gondwana in the Cambrian. So very, very long time ago, 550 million years ago, is when the sediments of the Magma group rocks were accumulating. And now, as we've mentioned, the Wilson cycle will start to come full circle, and that ocean basin will close via the development of a subduction zone. And so likewise, we can form passive margin sediments on the coast of Gondwana, and also passive margin sediments off the coast of Laurentia. These passive margin sediments off the coast of Laurentia will eventually form what we call the Humber zone, or the Humber terrain. So those sediments will accrete during ocean closure and form sedimentary rocks. And so we see the convergence now of the dunnage terrain, which represent these island arc terrains, something reminiscent of Japan, for instance, approaching the east coast of North America. And this material is too chemically, compositionally inadequate, let's say, to subduct into the mantle, and it's also too buoyant, right? And so it will subduct, or will accrete. And so it accretes right here. And we see a little bit of an ophiolite stuck in between there because of the abduction of some units of oceanic crust. So abduction is reverse to subduction, right? It's kind of thrust up overland. And you can see here the development of the Gander terrain in between. So we have the accretionary wedge sediments right here, and the passive margin sediments off the coast of Avalonia, that microcontinental fragment. And those sediments will later accrete to form what we call the Gander terrain in between those. Here comes Avalonia across here. So that's going to be accreting as well. And eventually the Avalon terrain will accrete, which is the microcontinent Avalonia, which has accreted against the margin. And notice that during each one of these stages, the subduction zone architecture has to change a little bit, right? Because we're continually smushing all of this material together. And so what was once ocean basin right here that was subducting downwards, there won't be any more ocean basin left to subduct after Avalon accretes, right? So Avalon will accrete, and then a new subduction zone will be regenerated, will restart off the opposing coast of the Avalon terrain. At least that's the working model. And so here it is. Here's the regeneration of a new subduction zone off the opposing coast of Avalon, and the final continental convergence of Gondwana with Laurentia, closing the Iapetus for good. And what we see there now is the accretion of those Magma sediments that are now abut against North America. So eventually, when we begin to re-rift this continental supercontinent, it'll be right about here. And now Africa will go this way, and this material over here will be the new North America. And so in Nova Scotia, what we see is basically just the Avalon terrain and the Magma terrain exposed. But we see these terrains stretching along the eastern seaboard of the United States, of Canada, up into Newfoundland, and up into the UK and Scandinavia as well. So we can see those here in Canada. So we can see the Magma terrain, really the only place that we see the Magma terrain outcropping is right here in Nova Scotia. But we do see the Avalon terrain kind of continue downwards into the United States and upwards into Newfoundland as well. And so right here is what we call, or basically a big thrust belt that they call the Logan's Thrust. And so this is the suture zone. This is the suture zone of pre-existing North American material with allochthonous material. So what we have here is this autochthonous material of Nova Scotia, right? The material that was there before the rocks that are inherent to the pre-existing North America, and the allochthonous material, which are all of these accreted terrains. Amy asked, did they change the names, or are the ones in the States distinct terrains? That's a good question. I believe it's related to the same accretionary event. However, I'm not quite sure if it represented one continuous microcontinental fragment. It might have been, you know, kind of like microcontinental island chains, kind of like Papua New Guinea or, you know, Indonesia, even though that's an island arc. But that sort of idea, that kind of accreted together. But I'm not quite sure. That's something I've been meaning to look into and start adding to my collection, actually, are analogous material from the terrains that are in Newfoundland and in the United States to kind of complete that suite of rocks. So I want to show you this image here, which is basically just this flipped over on its side. And this introduces a few terms here, namely the Para-Gondwanan and Laurentian realm of rocks. So what do those two words mean? Well, the prefix para means adjacent to or around. So Para-Gondwanan realms represents terrains that were adjacent to or around or associated with Gondwana land. The Laurentian realm of rocks and terrains were either rock types or sediments that were associated with Laurentia. Okay, so there's the two definitions there. So Laurentian are sediments or rock types or terrains native to Laurentia, whereas Para-Gondwanan realms were these terrains or sediments associated with or around Gondwana. And so we've split these up now into here in this top image. So you can see the Para-Gondwanan realms, namely Avalon, Gander terrain, the Magma terrain. All of these are what we call Para-Gondwanan. They were kind of either sediment directly related to Gondwana or microcontinents or arcs that were associated, adjacent to or associated with Gondwana. Now, the Laurentian realms in blues here, what we see, are the Humber terrain and the original Laurentian margin rocks. So the Humber terrain is a Laurentian realm. Why? Why are the Humber rocks technically Laurentian?
They formed along the passive margin at the edge of Laurentia, which meant they probably came from the sediment that was on Laurentia.
Exactly. So the sediments there on the passive margin of Laurentia are terrigenous sediments from the erosion of Laurentia itself. So it's basically, you can think of those sediments as just basically crunched up Laurentia and put on a passive margin, right? Still Laurentian material. And so we call these para-Laurentian material or Laurentian realm terrains. And so that's the definitions there. You can see that Nova Scotia is very much in the Gondwanan realm of things because the sediments that made up the Nova Scotia Maguma terrain rocks are from the shedding of sediments from Gondwanaland, Africa. Right, and this bottom image here shows, again, para-Gondwanan terrains. So now this is just looking at para-Gondwanan terrains, but now in the context of Pangea's formation. So what we see here are terrains in the eastern Canada area, including the Avalon terrain right here in Nova Scotia and in Newfoundland, extending down into New England and the Carolinas, like we see right up here. Right, so here's that little fragment from New England. Here's the Carolinian terrain down here. Right, so the same idea. Those were microcontinental terrains that were adjacent to Gondwana that then accreted onto the margin of North America. And you can see those analogous terrains come up here through the British Isles and even in the Iberian Peninsula of Spain as well. Any questions about that? I basically wanted just to introduce you to these terms, Gondwanan, Laurentian, right? Obviously, Laurentian is Laurentia associated. Gondwanan is Gondwanaland associated. So let's take a look at some of these rocks. The Humber terrain, as we've mentioned, represents Cambrian, mainly Cambrian turbidite units, so turbidity current units, on the passive margin of Laurentia. So remember what a turbidite is, right? Along the continental slope and continental rise, you can often get mass wasting events and landslide events, forming these submarine fans. And in these submarine fans, we form these stacked graded beds. And in the context of turbidity currents, we call these graded beds Buma sequences, with coarser material at the bottom and then progressively fining upwards until we kind of stack those like a layer cake because of progressive sequential turbidity current events. And so what we see here are these stacked layers of rock. There's a person for scale. So they're tilted. They're very much deformed and tilted because of that Appalachian orogeny. And so these units represent what we'd expect to see on the continental rise or the continental slope, or even areas of the abyssal plain, which are these thin, fine-grained mudstone-like or sandstone-like beds. So fine-grained material. That looks something like this. So nothing too impressive here. It's basically just a fine-grained sedimentary rock. We see these more sandy units right here and right here, mind you. So this is more sandy, and then these blacker units are more muddy. And so we have sand, mud kind of coalesced into now one sedimentary rock, which represents the terrigenous sediments shed off of Laurentia, constituting the Humber terrain. So nothing too incredibly impressive here when you look at these rocks. They're kind of just rather homogeneous, muddy to sandy sedimentary rocks. So what we see here as well as associated with the Humber terrain is evidence of one of those mass wasting events. So here at Cowhead in Newfoundland, so the Humber terrain, remember, it can extend across Atlantic Canada. So we see the Humber terrain not only in New Brunswick, but also in the northern flanks of Newfoundland as well. We don't see the Humber terrain in Nova Scotia. Nova Scotia is too far outboard. So we only see the Humber terrain in areas of, at least with respect to Atlantic Canadian provinces, New Brunswick and Newfoundland. And so the Humber rocks here in this particular area, we see a debris flow associated with those mass wasting events. And now in this particular debris flow, this was obviously a very substantial mass wasting event. We see enormously large clasts here. And now these clasts may have represented pre-existing layers of rock that were fractured and fragmented either due to a seismic event or incredible mass wasting. Likely a seismic event related to the Tectonic orogeny, one of those sub-orogenies underneath that Appalachians. So as the first units of material were accreting against Laurentia, this is what we call the Tectonic orogeny, very early Appalachians. You can think of the Tectonic as that. And so we see direct evidence of that there. As we move into Newfoundland a little more, we see evidence of the ophiolites as well, that outcrop. And now what we see here is the very top of one of those ophiolites. So all of this material right here are pillow basalts. And you can see that kind of pillow morphology to them, right? This kind of globular look. And so this represents pretty much the top of an ophiolite sequence. And so this is all tilted, as you can see here, right? A very substantial tilt to these rocks. And so as we move in this direction, we would see sheeted dikes, gabbro, and then peridotite eventually in that direction, depending on the structure of that. Maybe it's a big syncline and you'll see it outcrop somewhere else, of course, right? But generally speaking. So which way is this striking? If I were to take a look at these sedimentary beds, are they striking, relatively speaking, are they striking into the page or out of the page? Give or take. Out. Interesting. So let's stand up here. Right, and let's take a look at this bed right here. These are all stacked beds, right? So if your right hand, palm down, your fingers go very steeply down that dip, and it goes in. Yeah, this is a little bit of a confusing image here to view, but just imagine putting your palm, your right hand palm, right on this bed. Like if you could put your hand right there on this bed, your thumb would point basically away from the page, give or take. Obviously, it would kind of point at an angle, an oblique angle in towards the page, but yeah, in give or take. And so what we see on top of these ophiolites represent strata, overlying sedimentary units of rock that have accumulated on top of those pillow basalts, obviously before it was tilted. Right, the law of original horizontality would state that these sediments were deposited horizontally and then lithified horizontally and were basically later tilted due to deformation, related to those orogenic events associated with the Appalachians, in this case, the Tectonic. So we move away from the Humber now, a little more outboard, and we get into the dunnage terrain. And the dunnage terrain, again, represents these volcanic island arc units. So as we move from the Humber into the dunnage, we'd expect to see the absence of these deep water sedimentary rocks like Buma sequences and turbidites and volcanic rocks. Right? And this is exactly what we see. And so as we move into the dunnage terrain, this image is just south of Bathurst in New Brunswick, we see volcanic rocks. And so what these rocks represent are these kind of volcanic ash flow, debris flow units from volcanic activity. That might look something like this. So this rock right here is the result of volcanism. Now it looks very suspiciously like a sedimentary rock, but that's because ash can kind of behave like a sediment, right? Ash, through volcanism, can essentially be billowed out of a volcano and accumulate, much like a sediment can accumulate. So this material here is ashy material resulting from volcanic activity. And you can even see the layers in that ash, and you can see these little crystals. And these are called xenocrysts, and these tiny little crystals were ejected from that volcano. There's a lot of energy involved in volcanic activity. So all of these crystals were fragmented, were broken apart, and accumulated in this ashy rock. This is a volcanic rock that if you passed by in the field very quickly, you'd think was a sedimentary rock. And you shouldn't be ashamed by that. I would probably think the same thing until I sampled it and took a closer look. Geology's tough. This one's a little bit easier to identify as a ashy volcanic rock. Now, this is quite red because it's rather iron rich, and that iron has oxidized to form iron oxide. In this case, basically hematite, which is red, the same mineral that makes Mars red. And again, what we see here are little fragments that were ejected from that volcano, and all sorts of tiny little crystals and ash particles. And so this is also an ash flow rock. And here's the exposed weathered surface there. So that's what you would essentially see in the field. Pretty difficult to determine what the hell that is in the field, isn't it? And so as you see more and more of these rocks, there's really one surefire way to become a good geologist, and that is look at a shit ton of rocks. The more rocks we look at, the better we understand the diversity and what we'd expect to find in that location, right? By kind of understanding the tectonics of that environment as well a little bit. But, as a geologist, eventually you might pick up a rock like that and say like, oh, this looks like a sedimentary rock or maybe a volcanic ash flow. Now, where am I relatively speaking? Maybe I'll look at this rock over there and compare them. If I don't see sedimentary structures, if I don't see, ripple marks or cross beds or clear evidence of sedimentary depositions, then this is probably an ash deposit. Likewise, maybe I'll see xenocrysts, tiny little crystals and fragments that are ejected from a volcano called pyroclastics. And if I see clear evidence of pyroclastics, well, that tells me that this rock is volcanic in nature. And you get a really good feel for that by just looking at lots of rocks. That's really the take-home message, right? You become a violin virtuoso by playing a lot of violin. And likewise, you become a good geologist by looking at a lot of rocks. Here is Sugarloaf Mountain, as I mentioned. So this is a volcanic plug, a large volcanic plug that would have represented a small magma chamber, resulting from hydration melting via subduction underneath these terrains as they were being accreted. And so that's what this represents. I believe there's a ski lodge in the area, ski snowboarding lodge. So then we move down into the Gander terrain, and now we enter more sedimentary rocks. And these sedimentary rocks would have been the active margin sediments off the coast of the dunnage terrain, the subduction zone there, and also passive margin sediments that were off the coast of the Avalon terrain, as the Avalon was converging with the dunnage terrain. And so likewise, very similar to the Humber terrain, we'd see characteristic passive margin sedimentary rocks, rather fine-grained, sandy to muddy in nature. And this is near Grand Falls, New Brunswick, not too far from Fredericton. So if you're driving up to Edmundston from Freddie, you would pass by these rocks right here. Now moving a little more outboard, we enter the Avalon terrain, which represents the accretion of Avalonia, the microcontinent. which we see exposed here in Nova Scotia, in parts of Newfoundland, and in parts of New Brunswick as well. And so here are some Avalon rocks from the Avalon Peninsula of Newfoundland near St. John's. You can see that these again are very tilted rocks due to the Acadian orogeny now. So a little bit later, it's all part of the same Appalachian origin, remember, right? But it's kind of split into fragments based on what's accreting. And so we see these steeply dipping beds in that way. So in this image, which way are those rocks striking, in or out? Yeah, bingo, exactly, guys, in. All right, stand at the top of that cliff. Imagine putting your hand down those dipping beds. Your thumb should point into the screen. Now, these rocks in the Avalon terrain are host to some of the oldest multicellular complex fossils on Earth from a period known as the Ediacaran, which predates the Cambrian. So lots of fossils, complex fossils, kind of came on the scene in the Cambrian. So the first period of the Paleozoic era in the Phanerozoic eon, right? That's when we started seeing kind of the kickoff of complex life. But just before that, 600 million years ago or so, so maybe 40 to 50 million years before the Cambrian explosion, is when we started seeing the very first evidence, at least the first fossilized evidence, of these complex organisms. Now, these organisms were rather simple by today's standards. They were kind of like these sea fans that will kind of wave around on the ocean floor. So all organisms were essentially marine at this point in time. Everything got its start in the ocean. So these complex organisms are also marine. Nothing has made its way to land just yet. And so this represents one of those kind of broad fan-like leaf type of things that would have been on a stalk and would kind of wave around like a hand on the ocean floor, kind of skimming the ocean waters for nutrients. And we can see these at Mistaken Point right here. And so you can see some geology students walking along the outcrops there at Mistaken Point. This is a UNESCO World Heritage Site now, and you have to get permission to enter the site, and you have to remove your shoes and wear special booties to walk along these rocks. Very protected rocks now. Now we move down outboard a little bit more to the Magma rocks. So these are the last units to accrete onto the Laurentian margin, and the very last kind of sub-orogeny associated with the Appalachians, known as the Alleghenian, or the Neo-Acadian, depends on which literature you read. I'm not too worried about you guys knowing the nuances of all of these sub-origins, okay? I want you to be familiar with the Appalachians and what accretion is and the terrains that accreted. If you say the Magma is from the Alleghenian and this is from the Tectonic, I'm not too worried about that. I just want to exemplify that we can split these orogenic events into kind of sub-origins based on what's accreting and when at the time. Okay, so the last units to accrete accreted in the Nova Scotian literature, we usually refer to it as the Neo-Acadian. So the Acadian and then the Neo-Acadian. In the American literature, they usually refer to this as the Alleghenian orogeny. It's the same thing, essentially. It just depends on where you work as a geologist and what's the common expression for these terms, which, yes, admittedly, is very confusing. But let's just think of this as late Appalachians, when the Magma terrains were accreting. And these are some of the rocks that we see near Blue Rocks, near Lunenburg. So we can see that they're very, very highly deformed. Now, not in the case of folding in this case, mind you, but you can see some very, very clear rock cleavage. So we see two fabrics here. We see the sedimentary bedding in this direction. That's the primary sedimentary bedding. But we see the rock cleavage in a perpendicular direction. You can see that the rock cleavage is running this way. So you can imagine right here, if I were to take a sledgehammer to this right here, that would kind of break off like a sheet, right? Like a planar page, kind of like slate. It is slate, essentially. And so this cleavage, this fabric, is the result of those compressive stresses. Right? As we're squeezing these rocks together, all of the minerals that are kind of shaped like my hand tend to align themselves, generating rock cleavage. So we see the bedding there, but we also see the formation of cleavage. And the formation of rock cleavage is direct evidence of deformation compressive stresses, in this case related to the Alleghanian or Neo-Acadian orogeny, late Appalachian orogeny. We can see that quite clearly here. So you can see two fabrics in this rock. This fabric, the bedding. So here's the bedding, the primary sedimentary bedding running this way. And you can differentiate those based on color, right? But if we look closely, if I flip this around now, you can see that there's fabric going in this way, right? You can see that they're kind of like sheets running in through here, right? So again, here's the primary bedding running this way, but the rock cleavage is running this way, in and out. So the cleavage and the bedding in this case are roughly perpendicular. And so we see two fabrics in this rock, and that's related. This is related to sedimentary deposition and bedding, and this cleavage right here is related to deformation in those rocks. Now, this is when rocks begin getting very complicated, because we could have many episodes of deformation overprinting each other. So we could have primary sedimentary bedding, and then one episode of deformation generating cleavage this way, and then maybe another episode of deformation generating cleavage this way, and those cleavages can interact to form lineations, which can be measured. It gets rather complicated in these very highly deformed rocks. And so remember lineation, right? We talked about lineation, we talked about strike and dip, measuring planar structures. So all of this becomes very important when we start getting into structural geology, trying to understand how fabrics interact. And so if I had a planar fabric this way and a planar fabric this way, right? Both of those fabrics represent episodes of deformation. I'm generating a lineation, right? The intersection of those planes. And so if I have multiple deformation events generating planar fabrics, I can measure that intersection of fabrics as a lineation. It gets really complicated. Okay, here are some more near Lunenburg, and now in this case we can see clear folding. But what's really cool about this view is that you can see the folding like this, but you can also see the rock cleavage running that way, right? This is exactly what we'd expect if we were squeezing the rocks like this. We'd expect the rocks to be folded, but also generating cleavage perpendicular to the compressive stress direction. Right? And this is exactly what we see here. It's very clear evidence of compressive, both ductile in the case of folding, but also brittle in the area as well. We also see faulting, reverse faulting. And so there's the term down there, Neo-Acadian orogeny, which is essentially the same as the Alleghanian, broadly speaking. And here are the South Mountain batholith rocks. So these are the rocks near the shoreline of Prospect, which isn't too far from Peggy's Cove. The same really, really massive unit of felsic granitoid rocks that intrude the Magma group rocks. And these were formed in the Devonian. And so to put all of this into context, here's the Appalachian origin down here in green. And so the American Appalachians down here, the Smoky Mountains of Kentucky and Tennessee, that's the Appalachian origin just in the United States. And as we run up into Canada, we get into, even just kind of bordering onto the Gas Bay as well, we can see it, but it runs right through New Brunswick, through Nova Scotia, and then up eventually into the Scottish Highlands and Scandinavia. And so I've outlined one thing here, the Maritimes Basin. So this is a Carboniferous basin that was being developed during the time of erosion and breakup of Pangea now. So coming full circle with the Wilson cycle, right after convergence and creation of Pangea in the Appalachian Mountains, we begin to get continental rifting again. And so we start to get the formation of rift basins in the area. And so in the area of Nova Scotia, we see direct evidence of the formation of these basins through different types of rocks, namely rocks that are associated with river and stream and lake environments, and rocks that are called evaporites, which represent the evaporation of seawater. So saline, salty seawater, if it's isolated and begins evaporating, we precipitate those salts. And as we precipitate those salts, we get salt depositions, right? And these are what we call evaporites because they are generated through water evaporation. I just remembered I didn't show you that gold yet. So I wanted to introduce that right here. So these rocks, you can see a vein in this case. So these quartz veins. Now this may or may not be a vein, but they look very similar to this. See these white units right here represent these quartz veins, and these quartz veins in the Magma group are often auriferous, meaning they contain gold. And I'm going to show you an image of that. So this is some gold I found myself, actually, when I was on a hike at the Ovens. I was waiting for some friends to show up, and I just started taking a look at some quartz veins and kind of popping them apart with my rock hammer, and I found this. So this is a piece of quartz, and if you look very carefully, you can see that little speck of yellow up there. So that's a little piece of gold in this quartz. Now I have a microscope here, so this will do a little bit better. So there is a little speck of gold. So all of this vitreous material right here, this glassy looking material, is quartz. This is just some weathering material on the surface there. And we see that little speck of gold. This was the first gold I have ever found in Nova Scotia. I was pretty fired up about it. Yeah, pretty cool, eh? And so, I mean, odds are you'll be able to find your own gold if you look carefully enough, especially in the area of the Ovens. The rocks are slates that are heavily cleaved. And so the cleavage almost acts kind of like a sluice. It kind of collects sediment in the cleavage planes. And so you can actually kind of scoop out the sediment, put it in a bucket, take it home and pan it, and you'll probably find appreciable amounts of gold in that sediment, if you don't find it in the quartz itself, that is. Okay. So in the Maritimes Basin, this started to develop right around here during the Carboniferous. So now during the Carboniferous, we had the complete construction of Pangea. Now Pangea was essentially completed, and we started getting slight pull apart basins. So we started getting a little bit of rifting and some rift basins occurring, but also back arc basins as well. So remember that, you know, just like the Japanese example, during convergence behind the arc or behind the origin, we can start getting areas that are slightly extensional or slightly compress the cratonic material, generating a little bit of a back arc basin there. I think I have an image of that. If I just shoot forward just a hair. Maybe not. All right, we'll get there in due time. So in the Carboniferous, about this area of Prince Edward Island, New Brunswick, Nova Scotia was covered in a shallow marine environment, and there were many river systems and stream systems flowing into this basin. So you can kind of think of these as, you know, an example, a contemporary example in the Rockies, right, where you have basically these mountainous rivers that are kind of running out of the rivers into these river valleys, like the Fraser River Valley, for instance, right? And so we have the convergence of all of these mountainous streams and rivers kind of converging into a basin or a rift valley. And so the same thing was happening here in the Carboniferous. And so during this period in time, this area of Nova Scotia was very wet, was very tropical, was very humid, and was generating its vast quantities of coal beds. So it was quite swampy, plenty of rivers, plenty of standing bodies of water. And so this is a perfect environment to start generating vast quantities of flora, which would eventually die, forming our coal beds that we know today. And so this is a little bit of a reconstruction regarding some of those basins. So we see some slight rifting here, some slight basinal development. And what we see here are alluvial fans. So that's what those represent. This is a little bit of an artist's reconstruction of what this area of the Maritimes Basin might have looked like during the Carboniferous. And so all of this area would be quite mountainous, and rivers would flow away from those mountains towards the rift valleys or the basin. And as they're doing so, they're forming alluvial fans, right? Remember what those alluvial fans are. It's depositions of sediment that are channelized and then enter or de-channelize and kind of spit out all of that sediment as a vast accumulation of sedimentary material. And so this is when the sediment of Joggins was being deposited. This is when the sediment that we find in the valley, the Annapolis Valley of Nova Scotia, was being deposited. The sedimentary sequences that we see at Rainy Cove were being deposited at this time as well. So the sediment that we find at that site I always talk about, Rainy Cove, those rocks are associated with this geological environment. And we're forming evaporites as well. So periodically this area is flooded and then the seawater retreats, but that flood water is trapped. And so as that flood water is trapped, it's saline, it begins evaporating and precipitates its salt load. And so associated with the Maritimes Basin, we find alluvial fans, much like this one here. We find these sediments, which we call fluvial or lacustrine sediments. And now fluvial is just a fancy way of saying stream or river related. And lacustrine is just a fancy way of saying lake related. So we use these words in geography, in geomorphology, in geology. Fluvial, river, lacustrine, lake. And so the sediments that we find at Rainy Cove, now in the form of these deformed sedimentary rocks, are fluvial and lacustrine sediments that were formed in this Maritimes Basin during the Carboniferous. One example of those rocks is this one right here. This is a rock called a conglomerate. And as we can see, it's lithified sediment. Some of the clasts are really huge. Look at the size of that boulder right there. And then some of it is the size of sand. So it's very poorly sorted. It's rather well rounded, right? They're nice and polished, nice and eroded. Some is very big, some is very, very, very small, some is kind of middle of the road in size. And all of this material is lithified together, right? That's a solid rock. This material obviously must have been transported by a very energetic river, right? A river with a very high competence, in other words, right? Because it's moving very big material and very small material in the same manner. But not only is it moving this big material, but it's acting to erode this material quite well. So it must be very energetic, right? These clasts are very smooth and polished and eroded and very large. So that river must have been of sufficient energy to mobilize this material. It very well could have been a glacier Haley. However, probably not glacial till, but meltwater generated as a result of glacial melting. So this could be, valley-type glacier melt in the Appalachians that were running out of the mountains, mobilizing this material and depositing it into braided rivers and into fans, into alluvial fans. So this material might represent or might have been mobilized by glacial meltwater. But if this was glacial till, we'd expect it to likely be far more angular, as opposed to this nice rounded morphology, which is generating by saltation of those boulders along in the bedload. So it's kind of rolling along as a bedload and kind of eroding and polishing the whole while. This is material that you'll find at Rainy Cove. This represents what's called the Wolfville Formation, these conglomerate and sandstone units that are over top of that unconformity at the Rainy Cove area. So this would be a fluvial sediment that is deposited by a river system, mobilized by a river system. And so just to show you that image again, this is the Wolfville Formation at the top here, this unit right here. That's the Wolfville Formation. That yellow dotted line is the unconformity, and this is what's called the Horton Formation. And so the Horton Formation is kind of fluvial to lacustrine sedimentary deposits, whereas the Wolfville Formation above are fluvial sediments. And we see evidence of coal. We see evidence of coal all over the place in Nova Scotia, Stellarton, Cape Breton Island. Here's a coal seam here from Cape Breton near Sydney. And here are those evaporites that we see around the Windsor area. We also see these evaporites extending up into the Antigonish area and even up into Cape Breton as well. So these evaporites represent a rock called gypsum. And now gypsum is a salt. It's a calcium sulfate salt. And so much like calcium chloride, much like potassium chloride, it will precipitate from that water as we evaporate the water. And so as you drive north on the 102 and you pass by Windsor, you'll likely see these large cliffs of gypsum. Those cliffs represent evaporite salt precipitation from the Windsor Basin. From the Maritime Basin, the Windsor Basin, which was evaporating seawater during the Carboniferous, and that's how we got this material. Now up near, and this is a very fragile piece, but I'll show you anyway, and we'll leave it there. Up near Walton, which is not too far from Rainy Cove, as we drive over a little bit more east from Rainy Cove, we get to an area called Walton, and we see the Windsor group outcropping there. And so this is gypsum. It's very, very fragile stuff. You can see it kind of just chips apart. So this is calcium sulfate that was deposited from evaporating water. But what we also see on here are rills. So gypsum is rather soluble in water. It's not terribly soluble, but it's definitely soluble, just like sodium chloride is soluble, although sodium chloride is very highly soluble. So calcium sulfate, gypsum, is quite soluble, and you can see that weathering surface right here. So you can see these kind of channels, these water channels. So it's basically like rills that form directly in the gypsum itself. These are solid. Pretty cool, eh? But yeah, super fragile. Just crumbles everywhere. Okay. Next year, I should really make a concerted effort to shorten everything else and extend these lectures, because there's so much we can talk about with respect to Nova Scotian geology and the formation of some of these rocks in Nova Scotia. But we'll leave it there today. And then all we have to do is, oh, actually, I'll show you Walton. while I'm here. I mean, might as well. Here's the slides for Walton. And so up towards Walton, we see gypsum, and we see gypsum and mud in between. So this is mud, and this is gypsum. And so there was a little bit of deposition of salt. So the seawater was evaporating and depositing gypsum. And then another infiltration of water came, brought in mud and sediment, and that deposited on top. And then the seawater evaporated again and deposited gypsum. And then another flooding event, infiltration, and brought in mud. And so we see these stacked cyclic events of flooding, evaporation, flooding, evaporation. And we see that stacked up right here through the rock record. So if I zoom in on that, you can see that really nicely. Gypsum, mud, gypsum, mud, gypsum, mud, very, very regular. And we see these beautiful gypsum roses, they're called. So a lot of sulfates do this. Barite also does this as well. That's a barium sulfate. Calcium sulfate does it as well. And they form these really beautiful kind of radiating crystal structures that are called roses, gypsum roses. And so we see that here near Walton as well. And we'll leave it there and pick off here next lecture. Any questions, anyone? All right. So far, so good. And let's open the chat here. Okay. And so we left off around here. We were talking about after the amalgamation of Pangea, shortly after, so in the Carboniferous, roughly contemporaneous with, as a matter of fact, the Maritimes Basin was also forming, and as basins do, they accumulate sediment. And so we have evidence of that basin formation here in the Nova Scotia area, as well PEI and New Brunswick as well. Now, in the geological record, the evidence that we have to suggest the presence of a basin in this environment are fluvial and lacustrine sediments, so sediments that are associated with stream and river environments, which are called fluvial environments, and lake environments, which we call lacustrine environments. So sediments that are associated with the mobilization by rivers and streams, and then deposition into lakes and swamps, those sorts of environments. We see those sediments at Rainy Cove. Those are the direct result of sediment deposition during this Maritimes Basin episode. But we also see evaporites as well. And this suggests that the Maritimes Basin was infiltrated by seawater, saline water, which then evaporated, precipitating mineral salts such as gypsum, calcium sulfate, periodically. So there was these kind of flooding and mud deposition events, and then evaporation and salt deposition events in a cyclic fashion. So we can see the cyclicity of this kind of flooding evaporation in the rock record as well. So in these environments, we see evidence of alluvial fan formation. So moderately well-rounded, quite poorly sorted sediment that's deposited via river and stream in these mountainous regions. Because remember, you know, this is still a demanding mountainous region. This is the Appalachians at their prime. So material is being eroded out of the Appalachians and being deposited into these valley and basinal settings. And so we see direct evidence of that at Rainy Cove. And now this was a long-lived event, because note that there is a unconformity here, an angular unconformity, and you can see that right through here, right? It's a very obvious angular unconformity, probably the nicest example of an unconformity here in the province, with these fluvial sediments of the Horton group vertical, pretty much almost vertical, and those are the sediments you see where the students are standing in front of there. So these are fluvial sediments deposited by river stream environments, and also lacustrine sediments as well. So it's a bit of a mix. At the top here, we see what's called the Wolfville Formation, which was deposited many millions of years later. There's a significant age gap between the deposition of the Wolfville Formation and the Horton Formation, because as you can see, the Horton Formation has been significantly folded, right? So we're basically looking at almost like a vertical limb of one of those folds. So the Horton Formation has been significantly deformed before deposition of those sediments at the top there, the Wolfville Formation sediments, which are associated with fluvial environments, so very, very energetic river systems. And the evidence of that is the presence of certain rocks called conglomerates, which, as I showed you last time, look something like this, which is really poorly sorted sediment, but really well-rounded. And so we would have to have a very energetic river with a high competence in order to move this material, such as these really large cobbles and also these tiny little grains of sand, and also round them, right? Because these are getting rounded and polished via erosion as a bed load, essentially kind of bumping along the bed of that river and stream. And so the presence of these rocks suggests something about the depositional setting and the transportation setting. We also see evidence that this was a very productive, ecologically speaking, productive environment. Nova Scotia was tropical, humid, quite near the equator during the Carboniferous, and we see evidence of that in the form of coal. And we see evidence of periodic infiltration of seawater and evaporation of that seawater in the Maritimes Basin in the form of evaporite sequences. And now these rocks themselves are called evaporite rocks or evaporitic rocks. And we call them that because they're generated via the evaporation of saline water. So with periodic flooding and then evaporation of that saline water, we get deposition of salt. And in this case, the salt is calcium sulfate primarily. So these white cliffs near Windsor are gypsum cliffs, making Nova Scotia one of the very important centers for gypsum mining in the world, actually. Nova Scotia is host to the largest open pit gypsum mine in the world. And gypsum's used primarily for gyprock, like drywall, but also some other industrial purposes as well. And so this image really nicely exemplifies that cyclicity between kind of infiltration of water, bringing in the muddy layers and the deposition of mud from that seawater, and then the evaporation of the seawater precipitating gypsum salt. And so we can kind of see those repetitive stacked layers. And this is near Walton, Nova Scotia, so not too far from Rainy Cove. As a matter of fact, you can see both of these outcrops in one day quite easily. And we see some beautiful features there as well called gypsum roses. So quite remarkable mineralogy and structure in this part of the province. And so let's take our time to kind of walk through the series of events that affected Nova Scotia, southern Nova Scotia in particular. So let's focus primarily on the Magma group and the Magma terrain of Nova Scotia, being this, the foot, if you will, of Nova Scotia right here. So we're going to be looking at this terrain in detail, the most outboard terrain of the Appalachian orogeny, and we're going to take a look at how the rocks and structures that we see today in Nova Scotia actually formed. Let's walk through a bit of a logic puzzle here. Okay, so firstly, obviously, we need to deposit sediments. The Magma group rocks are meta-sedimentary rocks. So as the name implies, they are metamorphosed sedimentary rocks. To form a sedimentary rock, of course, we need to begin by the deposition of sediment, of course, right? And keep in mind the principles of original horizontality. So these sediments are depositing horizontal or very roughly horizontally, and the law of superposition. So the sediments lower in the sediment pile are older, they were deposited first, opposed to the sediments higher up in that sediment pile. Where were these sediments being deposited? The Magma group sediments. What do they represent? Bingo, Steve, exactly. So this is sediments, these are terrigenous sediments that were being eroded from Gondwana land, Paleo-Africa, essentially. So these are sediments that are accumulating off the coast of the primeval Africa, Gondwanaland, in the Iapetus Ocean. So these are passive margin sediments. Now, sorry, I just noticed Lauren's question here related to unconformity. So let's just flip back real quick to this right here. And just to remind you, there are three different types of unconformities we've talked about: disconformities, nonconformities, and angular unconformities. Which one is this? An angular unconformity, bingo. And it's an angular unconformity because the geometry of the rocks are different on either side of that erosional surface. And so we can see that erosional surface I've outlined in red. So basically kind of like a break in the rock record and a discontinuation. So what that break in the rock record represents, what that red line represents, is a period of missing time. So there could be a period of missing time there anywhere from, a few millions of years to 100 million years or more in that rock record. Between the time that surface, this surface here, was eroded and the deposition of new sediments. So, once upon a time, this would have been the paleo surface, and you would have been able to stand right there. That would have been the surface, the erosional surface, and then new sediments are deposited on top of that surface. This is what an unconformity represents, and we call this an angular unconformity because the geometry of these rocks are different. They're vertically dipping here and broadly horizontally dipping here. Now, if these rocks below were in this orientation and the rocks above were in this orientation, we would call that a disconformity. The geometry is the same, concordant geometry. I hope that clarifies that just a little. You're welcome, Lauren. Okay, so we'll just pass through here. Okay, so we got the deposition of the sediments on the passive margin of Gondwanaland in the Iapetus Ocean. And now, during the accretion of that material, very late in the development of the Appalachian orogeny, otherwise known as the Alleghanian orogeny or the Neo-Acadian orogeny. Remember that we can kind of separate the Appalachian orogeny into kind of subcategories of orogeny, of orogenesis. These aren't, one step and done type of situations here. These are very much stepwise orogenesis. So we're accreting terrains kind of one or two at a time in periods, right? Which will eventually lead to the Appalachian orogeny, but this is very much a stepwise process. So the Magma group, being the most outboard terrain from the Laurentian margin, was the last to accrete. So it was the last to kind of get snudged up against Laurentia's margin. And during this docking of Magma against the margin of, in this case, Avalonia, or the new margin of Laurentia, they were being deformed. Right, this is a orogenic belt. This is very high compressive forces. We're thickening the crust, and we're deforming the crust in both brittle and ductile fashions. And so the folds and the faults that we see in the Magma group rocks are the result of this Alleghanian orogeny, very late in the Appalachian orogeny. And so this deformation, compressive deformation, generates fold structures. And so that's why we see the folds here. But also keep in mind, this is an orogeny, right? So the crust is thickening, and the crust is deeper in the orogenic belt, is getting hotter, and is under immense pressure. Those are two perfect conditions to metamorphose those rocks. So not only are we deforming them, but we're changing them slightly. And again, we're not going to get into the nuances of metamorphism, what it is specifically, but in essence, it's how we can change the rocks, both in fabric and in mineralogy, related to elevated temperature and pressure. And so this is what happened here in Nova Scotia. Now, the rocks in Nova Scotia are rather low grade in the area of Halifax, and they increase in grade as we move towards the southwest. So as we go towards Yarmouth, we see the Magma group rocks get higher and higher in metamorphic grade. which would suggest they're probably a little bit lower in that orogenic belt where the pressure and temperature are higher, generating higher grade metamorphic rocks. In the Halifax area, they're relatively low grade, however. And so now we've folded those rocks, and you can see some new minerals forming here as a result of metamorphism. So not only does metamorphism change the fabric of the rocks themselves, how those minerals are aligned with one another, in other words, but can actually change the mineralogy through the mineralization of brand new metamorphic minerals or the breakdown and conversion of pre-existing minerals. And so we can see evidence of that folding in the ovens. And this is why I wanted to find that 3D image for you guys. So there's yours truly standing here at the ovens right on the hinge of an anticline. And so what we see here is an anticlinal fold. I'm going to go right through my face. And we see that kind of wrap around here. So I'm standing basically right on the hinge. And so the hinge is right there. And so this is a true anticline fold because this has not been overturned. The lower sequences, so these sequences of rock are older than these ones, which are younger. And these represent turbidites. So imagine now, back on the passive margin of Gondwana land, this sediment is being deposited in these sequential turbidite flows. Right, these sequential landslide events, which are depositing sediments on the abyssal plain and the rise, the continental rise. And so remember what Buma sequences are. They're basically just these sequences of graded material. They're graded beds. And so when we're at the ovens, we can kind of see these stacked Buma sequences going from coarser grain material towards finer grain material. We see another little Buma sequence here. Going upwards. So some of these Buma sequences are thick, some of them are thin. It depends on the volume of material in that turbidite, on turbidity current rather. Okay, so I just want to quickly show you that 3D map. This is kind of like a 3D tour of Nova Scotia here. Okay, here it is. Okay, can you all see this map? Okay, right on. So this, let's go way over here. This is the ovens. Oh, geez, it's hard to manipulate this here. So you can come down on the beach over here, roughly over here. You can get down on the beach. Now you have to pay attention to tides because you have to kind of walk along this beach. And as the tidal water comes in, you'll kind of get cut off. So you have to either climb up this cliff or pay close attention to the tides as you visit this place. But what we can see in this view here are dipping beds. Right? You can see these beds kind of poking out on surface and they're dipping into the ground. So they're kind of coming out in this view here. So as we move down that beach, we see those beds here again. So we're basically on one side of the anticline here. The other half of that anticline has been eroded away in this view. So we're looking at kind of one limb of an anticline. But as we move further and further down the beach, the other limb is preserved, and we get to see that anticlinal structure really nicely preserved right here. So we can see this really tight anticline. And you can see all of this white material. So this is vein material, that's quartz vein material. This is where you can find gold-bearing veins, essentially, in areas like this. Not all of these veins contain gold. However, this is a historic gold district, so you can find gold in here. And that piece of gold I showed you the other day was from this location. And so we see this really sharp, tight anticline. And so this material over here then represents one limb of the fold, right? You'd expect this to go all the way up and over. And now we're kind of missing the top half of this fold, right? So we're kind of seeing the core, the heart of this fold. And if we move just a little further over here, we see this really nice view kind of looking down the anticline. So you can see these units here dipping this way and these units here dipping this way. So the strike on this side, is it out or in to the page on the left side of this anticline? Roughly speaking, exactly. Nice guys. It's out. If I move to the other side of the anticline, it flips. The strike goes into the page, right? And so the strike is flipping because the beds are changing dip orientation along either side of that anticlinal fold. And you can see the axis of that tight anticline really, really nicely here. Chevron fold hinge, they call it. A really remarkable place to go. Now, this is a little away from where the sea caves are. And so if you were to go to the sea caves, they're kind of like over here. And so you pull into the parking lot around here and you walk back up the street a little bit, and then you can kind of cut in off of this field and come down to the beach over in this area here, which is arguably more interesting geology than the sea caves, but the sea caves are also cool. Okay, so we folded that rock, and now pretty much contemporaneous with metamorphism. Now, I don't want to say exactly contemporaneous because it postdates it by a little bit, but let's say the peak metamorphic grade. So the peak metamorphism, meaning the maximum temperature and pressure these rocks experienced in Nova Scotia during the Alleghenian orogeny, was about 410 million years ago or so. 410 million years. The intrusion, so I'm just going to write that down. So we'll write peak, meta, roughly 410 million years ago or so, give or take. The South Mountain batholith, this unit here, intruded at about 380 to 370 MA. So shortly after, in the geological context of things, right? You know, a few tens of million years after is when the South Mountain batholith intruded into those metamorphosed, folded, deformed rocks. And so we see that represented by this, this pink body. And I've also drawn little examples of maybe some sills and some dikes. So here's a bit of a sill right here. Here's a dike right here. A dike would be something like this, which is cross-cutting lithology, cross-cutting strata, whereas a sill would be something like this, which goes concordant with strata. Remember, they're basically the exact same thing. It's just the geometry that changes the name. But what you see around that as well is this halo. This halo right here is what we call a contact aureole. You don't need to worry too much about this, but what this halo represents is basically a halo of metamorphosed rocks, metamorphosed again. So not only were these rocks metamorphosed once during the orogenic event, during the Alleghenian orogeny and deformation, but they were also metamorphosed again via the intrusion of this South Mountain batholith. This material is really hot, right? This magma is really hot stuff. And so on the exterior, by a couple hundred meters to a kilometer on the exterior of the South Mountain batholith, the temperature is sufficient enough to kind of cook, to bake those rocks. And so this is a style of metamorphism we call contact metamorphism, because the rocks are in contact with a hot body of igneous material. And so it's basically baking the rocks. And so these poor rocks right in this area here were metamorphosed twice in a rather short time span, geologically speaking. Okay, so now we got the intrusion of the South Mountain batholith. And during the intrusion of that South Mountain batholith, we are breaking up the Magma Group rocks in the vicinity. And if we break up the Magma Group rocks and integrate those country rock fragments into the intrusion, what are those called? Inclusions, exactly, or xenoliths, both are acceptable. And that's what we see here. So this is South Mountain batholith granite. And what we see here are fragments, inclusions of Magma rock. So therefore, this is a really beautiful example of age relationships, right? You can see this granite kind of wrapping around and filling in the gaps between these fragments of country rock. So these are xenoliths or inclusions of older pre-existing Magma Group rock that were broken up and integrated into this cooling material. This was magma at the time, and now this magma has kind of cooled around these xenoliths. And so these xenoliths here were exposed to extremely high temperatures, and so these have been significantly metamorphosed and have undergone anatexis. Notice that they're quite black, right? Because only the felsic minerals survived, essentially. Only the mafic minerals, sorry. Only the minerals with significantly high melting temperatures survived. The minerals that could melt in response to the intrusion of this material here melted via anatexis and kind of bled out into the system. And so these are significantly altered inclusions. If you looked at the mineralogy and fabric of these inclusions, it would look significantly different than the average mineralogy and structure and fabric of Magma group rocks. You can see some more of them there. And so those rocks that are baked, that are essentially cooked along the margin of that intrusion, generate a metamorphic rock that we call hornfels. Again, don't worry too much about that name. Just understand that it has been a baked rock, cooked rock. And so this is also quite different than the average average Magma group rock, because these have been baked and cooked. It looks pretty innocuous, right? There's nothing too special about this, but you can see these tiny little blebs, these tiny little spots. It's kind of polka dotted, right? So those tiny little polka dots, these tiny little spots, represent minerals that grew in response to that elevated temperature in that thermal aureole around that cooling intrusion. And so those little minerals we call cordiorites. And those are metamorphic minerals that form in response to contact metamorphism. But again, this is a topic for Geology 1200 in significantly more detail. So what we're trying to do today is walk through the rocks of southern Nova Scotia, but not get bogged down in rock forming processes. Okay, and so if that hornfels, that contact metamorphosed rock that I just showed you, you can find your very own, if you're interested in collecting some rock samples of your own, right here in the Halifax area. So the intrusion of the South Mountain batholith is basically just off the Halifax Peninsula. You can see the contact of this near Bears Lake, just off of the peninsula. And so if you head towards Spryfield or the Armdale Rotary or towards Beachville, you'll pass over the contact and into those South Mountain batholith granites. And so the contact is quite close to the Halifax Peninsula. And the contact aureole, so that zone of rocks that have been baked, is basically right here, right on the Armdale Rotary. So as you drive in through the Armdale Rotary and up Herring Cove Road, you'll pass by this outcrop right here. Perhaps some of you recognize it. The Armdale Rotary is just down here out of view. And so as you drive up Herring Cove Road towards Purcell's Cove Road, you'll pass this outcrop, and this outcrop is hornfelized rocks. These are rocks that have been contact metamorphosed by the intrusion just a few hundred meters away. And so they look like this. They pretty much just look like sedimentary rocks, right? We can see the primary sedimentary bedding in here. So this is sedimentary bedding we're looking at here. That's the primary bedding. But those rocks have been mineralogically altered by that cooling intrusion. So if we were to take a microscopic look at them, we would see tiny little minerals, new minerals that formed in response to that contact metamorphism. As you drive down Northwest Arm Drive or Dunbrack towards Spryfield, away from the highway towards Spryfield, you'll pass by this outcrop as well, near, I think it's called Witherrod Lake, near Long Lake, Witherrod Lake, that area. So as you're driving, you'll see the Magma group rocks dipping, and you'll see that they're being cross-cut by a dike of granite. So this granitic dike we see here. And so this is all granite right here, and these are the Magma group rocks out here. And we can even see these tiny little veinlets of igneous material kind of shooting out into the rocks. We also see inclusions. So those are inclusions of Magma group material that kind of broke off the wall there and got integrated into that dike material. Okay, so now we have at about 370 million years during the Devonian, we have the introduction of the South Mountain batholith. And now erosion can take place, of course, right? Erosion is taking place this whole while, mind you, but erosion took place after the introduction of the South Mountain batholith, and now we have the South Mountain batholith exposed at surface. Now, of course, it didn't form there, right? It formed in an environment like this, very deep in the crust, 5 to 10 kilometers deep in the crust. And so we're basically missing 5 to 10 kilometers from the geological record above the South Mountain batholith. And so what we look at today, essentially, is something like this, where we see the South Mountain batholith now exposed at surface all over the place in the province, like Peggy's Cove, for instance, right? You're walking on top of a magma chamber, essentially, or what was once a magma chamber before cooling and erosion. And so now we look like this, and we see evidence of this erosion through glacial striations, roche mountainase, and drumlins, right? All of that is evidence that this terrain has been glacially eroded. And so here is South Mountain batholith, exhumed, meaning that it's kind of been uplifted through isostatic adjustment, right, and erosion of the material above. And we see evidence of glaciation in the forms of striations, in the form of roche mountainase, like at Black Rock Beach in Point Pleasant Park, and in the forms of drumlins, like Citadel Hill and in George's Island. Question from Amy here, is the idea that a lot of erosion happened before the Ice Age or that most of it happened via glaciation? Good question. A lot of the erosion that we see here happened. So we're breaking this up into kind of two parts. We're going to move slightly more northwards into Magma group material that has been overlain by other sedimentary sequences. But what we see here is these rocks have been polished during the last ice age. So a lot of the geomorphology we see here in southern Nova Scotia is influenced directly by the last ice age. So during the last glacial maximum, 20,000 years ago or so, and then surficial sediment deposition after that. So a lot of the sedimentary features, the unconsolidated sediment landforms that we see in southern Nova Scotia today are very young features. They're very, very young features, geologically speaking. But if we move northwards into the Magma group rocks, we have a more sediment deposition there before glaciation kind of changed the landform. I'll show you what I mean in a moment. There's another view of those striations. In this view here, it's clear that there was two directions of glacial ice motion. So ice was moving in one direction, and then ice changed direction and started moving in another direction. And so in southern Nova Scotia now, we're pretty much left with this. We're left with this exact scenario where we see these deformed, metamorphosed Magma group rocks exposed at surface. We see the South Mountain batholith exposed at surface, and we see these very young landforms resulting from glaciation, such as these drumlins that I drew on here. However, there's more to the geological record than meets the eye. In southern Nova Scotia, we're missing these rocks. But as we move upwards into the area of Windsor and the Annapolis Valley, we find younger sedimentary rocks. I mean, older than glaciation, of course, but younger than the Magma group rocks and younger than the South Mountain batholith deposition. So let's move upwards now into the Annapolis Valley. So this is a bit of a cutaway. And so what we're looking at over here is South Mountain batholith. Here's the South Mountain batholith granites right there, called DG, which is a notation for Devonian granite. So the South Mountain batholith is a granitoid rock that intruded during the Devonian, so it's given this terminology DG. Now, this rock right here is Magma, is the Magma group rocks, and it's given this little symbol OH because it's that little symbol C thing is Cambrian. Cambrian Ordovician. So those sediments were emplaced during the Cambrian Ordovician, way back on the passive margin of Gondwana land, remember. Now they've gone through hell since their deposition off the coast of Gondwana land, but those sediments are of Cambrian Ordovician age. Now on top of that material, we see younger sedimentary sequences during the Ordovician to Silurian, such as this unit right here. So these are younger Silurian age sediments, which have also been deformed as well in conjunction to that Alleghanian orogeny. But we see significantly later units as well. So we see these Triassic units. This is the symbol for Triassic. So this is Triassic sediment. And now, if we think way back to when we were talking about the geological timescale, the Triassic began about 280 million years ago or so. The Silurian, much, much older, right? Around 400 or so million years. So there's a huge gap in time there, a huge gap in time. And what surface is this? What sort of surface is that right there? An angular unconformity, exactly. Look at the difference in geometry between those units, right? We have these deformed, folded units below, belonging to Ordovician Silurian age, and Triassic sediments above, with a significant gap in time there, right? Hundreds of millions of years of missing time between that. So we have the Triassic sediments depositing on top of that, and then during the breakup of Pangea, so as Pangea was rifting apart again during the late Triassic to early Jurassic, which is where these symbols come from, Triassic, Jurassic, we started getting rifting. And what happens when we have a divergent boundary and we get rifting? We get the production of basaltic magmas. Those basaltic magmas can flow to the surface, forming lava flows, forming basaltic lava. And this is what constitutes the North Mountain of Nova Scotia today. So if you're in the valley, so for instance, here's Wolfville right here. If you're right smack dab in Wolfville and you look to the south, you'll see the South Mountain batholith kind of rise up. If you look to the north, you'll see the North Mountain basalts kind of rise up. And right in the valley, you're sandwiched between Jurassic basalts from the rifting of Pangea, and to the south, Devonian granites resulting from essentially the amalgamation of Pangea. So it's like the south is the creation of Pangea, the north is the rifting of Pangea, right in the valley. So that's a cool little thing to remember next time you're in the valley. But these lava flows are kind of dipping as well. So they're overlying those Triassic sediments. What do you think those Triassic sediments represent? Why are they continuous, let's say? Why are they conformable with the Jurassic lava flows above? What do you think those Triassic sediments represent? Now keep in mind, we're beginning to rift Pangea here. What do you think? And now there was a hint at this way back in the lecture when we took a look near the Blomidon area where we saw those Jurassic lava flows overlying those red sandstone units. Does that ring a bell at all? Maybe. Where do sediments accumulate, firstly? Broadly speaking. Exactly. They accumulate in basins, right? So this is not quite an ocean basin yet, but it's a rift basin. Yeah, there we go. It's a rift valley. We're beginning to rift apart Pangea. And so we're forming these basinal environments, much like we see in East Africa today, horst and graben structures. And so these grabens, these depressions represent rifts. And so those Triassic sediments represent sediment accumulation in the Rift Valley that's beginning to form as Pangea is pulling apart. Shortly after rifting, we start forming flood basalts. And those flood basalts, if given enough time and the rift proceeds, will develop a an ocean basin, right? We'll develop a divergent boundary mid-ocean ridge sort of situation like we see in the Atlantic today. Now, this rift in the Bay of Fundy did not continue. It went extinct and the rift kind of proceeded off the coast of Nova Scotia, but it did proceed there initially, very early on in its formation. And so now the view kind of looks more similar to this. So we see South Nova Scotia right here. So we'll call it S and S. North Nova Scotia over here, the valley. And offshore over here. So obviously offshore, that's a passive margin sediment or passive margin setting. So we're accumulating sediments on that passive margin off the coast of Nova Scotia. And as we move up Nova Scotia, North Nova Scotia into the valley, we see Triassic and Silurian aged sediments and also Jurassic flood basalts as well. Now, this is very broad, right? I basically this figure lumps those Triassic sediments into one main unit. Now there's way more information we could pull apart here, right? It's just not one giant, thick, homogeneous unit of sediment. That's a lot of time in the Triassic. So, you know, we could pull apart the nuances of this Triassic aged unit in more detail. There's a lot more to talk about in Nova Scotia geology, but very broadly speaking, this is sufficient. Okay, how's everyone doing so far? That pretty much concludes Pangea and the formation of Atlantic Canada. Hopefully you have a little bit of a better appreciation and understanding of the geology that formed the Atlantic Canadian provinces and much of the east coast of North America in general. And so now as you drive towards Quebec, you're basically passing through these accreted terrains, which each represent their own unique story. They each have their own unique origin and story to tell. And so moving away now from Pangea, now that we've rifted Pangea in the Triassic to early Jurassic, we're right in the middle of a new Wilson cycle today as we speak, right? The Atlantic Ocean is still growing, so we still haven't kind of wrapped that corner and started converging and closing the Atlantic Ocean. So we're kind of right in the middle of a new Wilson cycle here. But during the Jurassic, shortly after the Jurassic, not only was the Atlantic Ocean forming on the east coast and Pangea was drifting apart, but over on the west coast of Canada, a lot of stuff was happening, including the accretion of the terrains that constitute British Columbia. And so this happened between 200 to 65 million years. So, you know, an appreciable amount of time for the accretion of these westerly terrains. And these constitute the Canadian Cordillera as we know it today. So we're right about here is where Pangea starts rifting. So there we go. We got rifting of Pangea. And now we have the introduction shortly after of the terrains that constitute British Columbia and the Rocky Mountains. And so the Rocky Mountains are still a rather young landform. It's still a rather young origin, right? Resulting from its accretion only about 100 million years ago or so, which is actually kind of just a blink in the eye, geologically speaking, for instance, right? So this is why the Rocky Mountains are still quite demanding. They're still a very significant mountain range because they haven't had enough time to erode like the Appalachian Mountains. The Appalachian Mountains have had, you know, 100 to 200 million years, if not more, time to begin eroding. So the peak of the Appalachians was basically complete by about here, right? So we've had all of this time to erode the Appalachians compared to the development of the Western Cordillera. Okay, so in stage 5, what we're talking about here is the breakup of Pangea. Stage 5 doesn't have a supercontinent to speak of, right? Because, you know, we haven't completed our Wilson cycle yet. So in stage 5, we're breaking up Pangea and opening the Tethys Ocean, which is kind of like an ancestral Indian Ocean. India still has not moved northwards significantly yet. So India is still hanging out down there by Antarctica. And it only is in the last 200 million years or so that India shot northwards and slammed into the Eurasian plate, forming the Himalayas, which are also of very young origin. The Himalayas are still growing, as a matter of fact. And so we're going to transition over to Western Canada. We're going to take a look at some of the landforms there, and we're going to briefly talk about the Western Interior Basin, which constitutes much of Alberta and Saskatchewan today. So here we are about 200 million years ago or so. Now we're starting to split apart Pangea. You can see the beginning of the Atlantic Ocean start forming right in there. The baby little Atlantic starting to rift apart. North America rifted apart from Northern Africa before South America did, which gives the Atlantic Ocean that kind of sinusoidal, wormy looking shape to it. And so we got the beginning stages of the Atlantic right there, and the Tethys Ocean, which is a divergent boundary in this case. You can see India still down here, hanging out with Australia and Antarctica. Australia will eventually move this way, Antarctica will move this way, and India will move that way, and eventually slam into the Eurasian plate, basically transforming the Tethys Ocean into what we call today the Indian Ocean. And so during this period in time right here in the Jurassic, this is a brand new rift valley. And so we call this in geology the Central Atlantic Magmatic Province, or CAMP for short. And so there was a lot of magmatic activity today. So imagine, you know, Iceland on steroids, essentially, right? Iceland is very volcanically active, spewing out huge quantities of mafic basaltic lava. This is what was happening in this part of Canada and Northern Africa during the rifting of Pangea, just boosted up to another order of magnitude. And so this is the event, the CAMP, the Central Atlantic Magmatic Province, that gave rise to the lava flows that we see today in the North Mountain, for instance, of Nova Scotia. And this was that view I was talking about earlier, where we see those Rift Valley sediments, those red Rift Valley sediments below of late Triassic age, and then those Jurassic lava flows above, which basically, you know, spew forth and kind of overlay those sediments below. What does a lava flow, what does the morphology of a lava flow imply about where that lava was ejected to the surface? Was it terrestrial or was it marine? Not underwater, exactly, terrestrial. If it was underwater, we'd expect to see pillow basalts, right? So lava flows are evidence that this lava was terrestrial, basically, or that it flowed on land and not underwater. And so we call those lava flows, of course. And so here's just for your reference, a little bit of a cartoon about the breakup of Pangea. So with very early breakup, we see North America start moving away from Africa. And then with development, we start seeing India move forward. So you can see India start trucking northwards here, closing off the Tethys, forming the Indian Ocean. And now we see South America start rifting apart from Africa, forming the Atlantic as we kind of know it today. India is still moving northwards in this view, closing off the Tethys. So take a look here, though, on the west coast. So over here on the west coast, we see the accretion of new terrains on the westernmost flank, the westernmost margin of North America during this period in time, 200 to 60 million years ago or so. So during North America's migration to the northwest, it was accreting terrains along the margin. So there's an active subduction zone, of course, along the west coast of North America, which still exists today. So the take-home message about the rocks out west are that these are very old rocks. These rocks are very, very old. Remember that the accretionary event, the origin, could in theory be young, right? The origin is young, but the terrains that are accreted might be very, very old, right? So these might be microcontinental fragments that are billions of years old, but have only recently accreted. And so what we want to remember is that these might be very old rocks, but very young landforms. And by landforms, we're talking about the mountains themselves, the topography itself, the folds, the faults, the mountains, and the features therein, right? Landforms, very young landforms resulting from orogenesis, but very old terrains that were accreted. Let's take a look at this YouTube video here. I forgot to load that up, so just bear with me. Any questions while I get this loaded up?
Does contact metamorphism create higher grade metamorphic rock?
Oops, sorry, Stephen. Good question. So metamorphic grade is primarily influenced by temperature. And so the higher the temperature, the higher grade metamorphic rock you get. And so, yes, in essence, you can see kind of a gradient in grade as you move away from the batholith. So right snugged up adjacent to the cooling intrusion are very high grade metamorphic rocks. And as we move progressively further away from that cooling intrusion, the metamorphic grade goes down, right? Because the temperature would be going down as well as you move away from that hot body of rock. So pressure primarily influences the fabric and structure of those rocks, but temperature influences the grade. And by grade, I mean the minerals that we find there. Certain minerals are only formed at very, very high temperatures. Certain minerals form at relatively lower temperatures. So by looking at the mineralogy of the rocks, we can kind of garner some information relating to the maximum temperature those rocks were subjected to. And so we might find the exact same high grade minerals in rocks that have been subjected to contact metamorphism, and also in rocks that are very, very deep in the heart of an orogen, which have also been subjected to very high temperatures. But we would expect the fabrics of those rocks to be different, because in the heart of an orogen, very high pressures persist, which can really change the fabric and the structure of those rocks. But the grade might be pretty much the same, essentially. Yeah.
Cool, okay, thank
So
you.
we'll talk more about that in Geology 1200, which is a really, really interesting topic. Metamorphic rocks, they're very complex, but super cool and very beautiful rocks.
Awesome.
I hope you're taking 1200, are you?
Not currently,
but like in September?
In the September, I'm planning on it, yeah.
Excellent, good to hear. Okay, so let's share my screen here and watch this video. Okay. So we're in the Cretaceous now. So we're a little bit past the Jurassic. As you can see, the Atlantic Ocean is forming. Right? We see the baby Atlantic Ocean forming here, at least the North American portion of it. So it started as a narrow seaway, right? And we see Nova Scotia and Newfoundland here and New Brunswick here. Obviously, it doesn't look exactly the same as it does, but similar. So let's play, and we're going through Cretaceous. So you can see this terrain here, the Stachynia terrain of Western North America begin accreting. And so this ocean basin in between is beginning to close. We're beginning to form a continental arc in this area right here. There's a continental volcanic arc forming because of that ocean closure, giving rise to a lot of magmatic activity that we see in the Rocky Mountains. There we go, we have accretion of that. And so late Cretaceous now, the dinosaurs are almost extinct. They still have a couple or a few tens of million years to go here. So during this period in time, as you can see, sea levels were substantially higher. And so much of central North America was flooded by a shallow marine environment. And this is where we have a lot of the features that we see in Saskatchewan today. The reason why Saskatchewan and Alberta and Manitoba are so flat and enriched in these sedimentary packages is because they were a large basin. During 80 million years ago or so, Saskatchewan was completely underwater and thus accumulating these marine sediments. Not only that, but Saskatchewan is really rich in a mineral called potash, which is an evaporitic mineral that forms via evaporation of these shallow marine basins. So periodically Saskatchewan was flooded and then evaporation was proceeding. And now when I say evaporation, I don't mean that it's drying out completely and then flooding and drying out completely and then flooding. A partial evaporation of that constrained basin can lead to precipitation of salts, right? Like if I had a glass of water full of salt and I evaporated half of that water, I would precipitate salt, but I didn't need to get rid of all the water, right? So the same principle is true here. So this is what forms now this Western Interior Basin, which is Saskatchewan, parts of Alberta, and New Brunswick. You can see the Maritimes were pretty flooded as well. Much of the Maritimes were underwater here. See little parts of Cape Breton Island sticking up in southern Nova Scotia. So the dinosaurs are now extinct, and mammals come on the scene. We still have a little bit of a shallow basin right here in Saskatchewan. Notice there's a divergent boundary that's also present between the Canadian Arctic archipelago and Greenland, which you probably noticed in one of your labs, as a matter of fact. There's a divergent boundary that was present there that separated Greenland away from Baffin Island. And now we see the Maritimes kind of a little more familiar. But what we're seeing now is sea level go down. So now we're seeing sea level go down, and the entire Grand Banks essentially is above water, right? So the Maritimes is this kind of one continuous land patch. Sea level rose back up again, and now we see it begin to flood. So about this period in time right now, is when we had significant glaciation as well, as you can see in the northern half. So sea level plummeted, and we see lots of land being formed. Look at Florida, look at the Grand Banks around Newfoundland. Here's the last glacial maximum, so pretty much almost current day, and there we go. Now we're current day. Notice the Great Lakes formed after the retreat of that glacial body. Okay. Okay, so what we saw there was periodic flooding of the interior of Canada, generating these kind of shallow marine environments. And this is what we call the Western Interior Sedimentary Basin, where this being a basin was obviously accumulating sediments and evaporitic sequences as well through the evaporation of that seawater. And now this is technically a foreland basin, essentially. So remember those, the architecture of these basins around volcanic arcs or around orogens. Now, this isn't necessarily an arc anymore, and so we can have these kind of foreland basins that are forming here, which would be analogous to a kind of a back arc basin, you can kind of think of it as. We're not going to get bogged down in sedimentary architecture or anything like that, but I did want to stress that this was a basin at the time of formation. So I mentioned that, I think last time I mentioned that, not only are we forming a basin, say, let's imagine Japan again, not only are we forming a basin because we get a little bit of extension there behind the arc, so this kind of back arc extensional environment generating a bit of a basin. But what happens in with respect to accretion and continent-continent conversion is that these accreted terrains are adding mass to that cratonic fragment. They're adding mass to that plate. And so that mass is isostatically adjusting that plate and will push that plate downwards. And so you can see in this cartoon down here that North American craton be kind of depressed downwards a little because of those accreted terrains that are thrusting up on top of that older craton. And so it's kind of warping that craton down through isostatic adjustment. That warping downwards can generate a basin, this foreland basin right here. So this kind of downwards warping is generating a little bit of a depression there, which can act as a basin, accumulating sediments that are shed off of those mountains as they're eroding. But we also have forearc basins as well, of course, right? So we're getting sediments input into the forearc as well. And this back arc, which in this case is not a back arc because it's not this not a volcanic island arc situation, so it's a foreland basin, we call it. There's all sorts of dinosaur fossils in this area as well. Very good environment for preserving fossils, right? These sedimentary basins, because in order to preserve fossils, we have to bury those organisms quite rapidly, or else they're just decomposed and eaten away, right? So we need to we need a mechanism to bury those deceased organisms quite rapidly. And so here's the KT boundary when those dinosaurs went extinct. And so during the extinction of the dinosaurs, you can see that kind of shallow marine basinal environment here in the center of the North American continent. And if any of you have been to Alberta, you maybe have gone to the Dinosaur Provincial Park or Drumheller Provincial Park, where there's all sorts of really, really remarkable dinosaur fossils preserved. And one of those fossils was named after the province itself, Albertosaurus. And so how do we know that the dinosaurs went extinct via this impactor at this period in time? Well, we can find evidence in the form of iridium in the rock record. Now, as I mentioned in the past, when we were talking about carbonaceous chondrites and meteorites, these are rather enriched in the element iridium, which is essentially the rarest, if not the rarest, the top 3 rarest elements on Earth. It's a very, very rare element. And so if we see an enrichment of iridium in the sedimentary layer, that suggests a meteorite impactor, because meteorites are actually relatively enriched in iridium compared to the crustal rocks of Earth. And so if we see an iridium-rich layer, that's evidence that that is basically fallout, sedimentary fallout from that impactor itself. It's basically pulverized meteorite that's kind of raining out and forming this very thin sedimentary layer. And so you can see that spike right there. Notice the extinction of animals. So planktonic organisms took a massive dive at about this time. The climate took a significant dive in temperature at this time, and that corresponds almost perfectly to a spike in iridium right at that period of time. So I encourage you guys to watch this video. It is a big tectonic reconstruction. As a matter of fact, I was going to spend a little bit more time. Where are we at here? Okay. So now we're just talking about the last few tens of million years, which was a result of glaciation. Canada, as we know it, is a result. The landforms on Canada, at least, are primarily a result of glaciation. The Great Lakes, the Rocky Mountain valleys that we know, the morphology of the Rocky Mountains, the morphology of the coastline of eastern Canada, the fjords, Halifax Harbor, the drumlins. This is all a result of a very late stage glaciation. And so I'd like to ask a question. Do you want to take a look at this video, or should we spend the next 10 minutes going over some examples of strike and dip notation and symbols? Doesn't really matter much to me. What do you guys want to do? Team video we have for one. Any other votes? Okay, 2's a crowd, I guess. 3's a crowd. There we go. Okay, so we're all for the tectonic reconstruction video. That's abundantly clear, I think. So next week during the tutorial, then we'll go over strike and dip symbols, notation, and the symbols then. So let's wrap it up with a cool video. Let me just get it queued up. Okay, here we go. So this is made by a researcher, a tectonic researcher by the name of Christopher Scotis. And a lot of the reconstructions that you see, these tectonic reconstructions, are pretty much made by this guy. If not made by this guy, made in collaboration with this guy. He is a world famous tectonic geologist. And he makes these really, really remarkable videos. Well, that was odd. Okay. Is everyone okay? Everyone sees this? Okay. So I think this starts like way back. Let's see when this starts. Okay, it starts at the Cambrian. So this is from Cambrian to present day. And he clearly likes classical music because almost all of his videos are queued up to classical. So Rodinia is breaking up now. This is Rodinia, and it's starting to rift apart. We see Laurentia, we see Baltica, and Siberia right here. This is an island arc, the volcanic island arc here. So there's a subduction zone right here, and it's forming this island arc complex. Here come some of the terrains on the east coast accreting. So the east coast is starting to be constructed now. You can see the Magma group there, little Nova Scotia at the bottom there, start slamming in. So now we're starting to close the Iapetus Ocean, fully, that is. So we're closing the ocean here, and obviously there's subduction, so there's active volcanism, and we're forming continental volcanic arc in Nova Scotia, or in New Brunswick primarily, but we see that evidence of volcanism in New Brunswick. So now we pretty much have Pangea, minus a couple little floating parts around the area here, but Pangea has kind of come together here during the Carboniferous. Now I want to pause it right there for a quick second. Notice the depression right through here. There's a bit of a depression now. I think I paused it a little too late, but here we have the maritime basins start to form. So this kind of basinal environment right in through here, where the Appalachians are shedding their sediment and depositing those lacustrine and fluvial sediments in that basin during the Carboniferous. Notice how close Nova Scotia is to the equator as well. So during the late Carboniferous, Nova Scotia was pretty much right on the equator. So Pangea is complete, of course, and you can see that kind of white stripe across the middle of Pangea representing the Appalachians, or the Trans-Pangean Mountains. We're going to begin rifting Pangea apart now very soon in the late Triassic. It always blows my mind to think that, you know, vast quantities of organisms were living on this and roaming around. Dinosaurs were walking around on a planet that looked like this. It blows me away. To go back in time and be a fly on the wall, eh? Just watch. So here we go. We're starting to develop the Central Atlantic Magmatic Province. We're getting continental rifting, and you can see that start beginning right about here. So we start getting this narrow seaway and infiltration of seawater into this rift valley. You can see northern Africa pretty much snugged up right against Nova Scotia. That is getting crescendoing here. And here we go. The Atlantic Ocean starts forming. You can see Morocco start pulling away from Nova Scotia. Gulf of Mexico was forming. What I found interesting here as well is that the Yucatan accreted onto Mexico. So Mexico never really contained the Yucatan Peninsula. It kind of accreted on that pretty late in the game. I didn't know that. So now in the Cretaceous, Middle Cretaceous, we start to see the southern half of the Atlantic Ocean begin forming. South America is starting to rift apart from Africa. And so this is why we have this kind of weird shape to the Atlantic Ocean, right? Because it didn't rift all in one linear fashion. It rifted apart in stages. So we see that kind of sinusoidal flow to the Atlantic. There's India. There's a little India making his way north. I might have missed it, but I think the western terrains have already accreted. Okay, I missed that. I was preoccupied with the Yucatan Peninsula, apparently. There goes Australia over as well. India is starting to really truck northwards now. So the Tethys Ocean is now closing because India is moving northwards, and we form the Indian Ocean. So now the Tethys and the Mediterranean were one main ocean called the Tethys. But once India moves northwards and Africa moves northwards and close off that strait, we form the Mediterranean and separate the Indian Ocean from that. So now mammals are on the scene. The dinosaurs are extinct. The beginning stages of the Himalayas start to form. Africa is still moving northwards, and there's evidence of Africa moving northwards due to the seismic and volcanic activity in Italy and Greece, right? This is a result of Africa moving northwards and subducting Mediterranean underneath Europe. And so there's the Himalayas. North America is pretty much complete. You can see all the island arcs around Indonesia, Philippines, Papua New Guinea start forming around here. Ice Age, and now today. And there we have it. Okay, everyone. Well, that concludes the course material. It was an absolute pleasure teaching all of you. I had a lot of fun. I hope you guys did too, relatively speaking. I mean, it is a course after all, so it can only be so much fun, I suppose.